The question of whether the universe is infinite has fascinated scientists, philosophers, and thinkers for centuries. Our curiosity about the cosmos drives us to explore the vastness of space and understand its limits, if any exist. This quest has led to some of the most profound discoveries and theories in modern science. From ancient civilizations to modern astrophysicists, the nature of the universe has been a subject of intense debate. Ancient myths and early scientific theories offered diverse explanations, each attempting to answer whether the universe has an end or goes on forever. These early ideas laid the groundwork for our current understanding. In the observable universe, we can see millions of galaxies, each containing billions of stars. This vast expanse, however, is only a fraction of what might exist beyond our observational capabilities. The limits of our technology mean we can only infer so much about the universe's true size. The cosmic microwave background radiation provides a snapshot of the early universe, offering clues about its size and shape. Discovered in the 1960s, the CMB has been crucial in shaping our understanding of the cosmos. It tells a story of a universe that began with a Big Bang and has been expanding ever since. The Big Bang theory is a cornerstone of modern cosmology. It describes the universe's origin and its subsequent expansion. Evidence supporting the Big Bang, such as the CMB and the redshift of galaxies, suggests a dynamic and evolving universe, possibly infinite in extent. Dark matter and dark energy are two mysterious components that make up most of the universe's mass energy content. Their presence and behavior influence the universe's expansion, raising questions about its ultimate fate. These enigmatic substances challenge our understanding and hint at a possibly infinite cosmos. The universe's shape and geometry are critical in determining whether it is infinite. Theories propose it could be flat, open, or closed, each with different implications. Current evidence leans towards a flat universe, which might suggest it is infinite, but this is still a topic of active research. The expansion of the universe, discovered by Edwin Hubble, reveals that galaxies are moving away from us, suggesting the universe is growing. The rate of expansion, driven by dark energy, affects our perception of its size and potential infinity. This ongoing expansion complicates our understanding of the cosmos. Multiverse theories suggest that our universe might be one of many, each with different physical laws and properties. These theories expand the concept of infinity beyond our universe, proposing an endless number of parallel universes. While controversial, they offer intriguing possibilities. Philosophical and theoretical implications of an infinite universe challenge our understanding of reality. The concept of infinity brings paradoxes and thought experiments that stretch the limits of our imagination. Philosophers and scientists alike grapple with these ideas, seeking a deeper understanding. The current scientific consensus on the universe's size is based on the best available evidence, yet it remains tentative. Leading theories and models suggest a vast, possibly infinite universe, but new discoveries continually reshape our understanding. The scientific community remains open to new ideas and evidence. Ongoing debates and research in cosmology reflect the dynamic nature of the field. As new technologies and methods emerge, our ability to observe and understand the universe grows. These advancements bring us closer to answering the question of whether the universe is infinite. Predictions for future discoveries in cosmology are both exciting and uncertain. With upcoming missions and telescopes, we hope to uncover more about the universe's true nature. Each discovery adds a piece to the puzzle, helping us approach the ultimate question of infinity. Personal reflections on the universe's size and nature highlight our place within it. The vastness of space can be both humbling and inspiring, prompting us to continue exploring. Our quest for knowledge is driven by the desire to understand our cosmic home. As we explore the universe, we are constantly reminded of the complexity and beauty of the cosmos. The search for an answer to the question of whether the universe is infinite is a journey that spans both time and space. This journey, filled with discovery and wonder, continues to inspire us. Understanding whether the universe is infinite holds profound significance for our comprehension of reality. It challenges us to think beyond the confines of our planet and our solar system, expanding our perspective on the cosmos. The question impacts our understanding of physics and the fundamental laws governing the universe. If the universe is infinite, it might imply different principles than if it were finite, affecting theories from quantum mechanics to general relativity. This inquiry influences cosmological models that describe the universe's origin, evolution, and eventual fate. It drives scientists to develop more precise models and refine existing theories, leading to a deeper grasp of cosmic phenomena. Philosophically, the concept of an infinite universe stretches our minds, inviting us to ponder existence, infinity, and our place in the cosmos. It brings forth questions about the nature of reality that have intrigued humans for millennia. An infinite universe could imply an infinite number of possibilities, including other worlds, civilizations, and perhaps even versions of ourselves. This notion fuels the imagination and speculative thought, inspiring science fiction and philosophical debates. The search for an answer stimulates advancements in technology and methodology. To probe the universe's limits, scientists develop cutting-edge instruments and techniques, pushing the boundaries of what we can observe and measure. Understanding the universe's size has practical implications for space exploration and future human endeavors. If the universe is infinite, it could shape our approach to exploring and potentially colonizing other worlds. The question also influences our understanding of time. An infinite universe might suggest an infinite past and future, altering our perception of time's flow and its implications for existence and continuity. From a theological perspective, the nature of the universe intersects with beliefs about creation and the divine. Different religious and spiritual traditions offer various interpretations of an infinite cosmos, enriching the dialogue between science and spirituality. The pursuit of this knowledge fosters international collaboration among scientists, uniting efforts across borders to answer one of humanity's most profound questions. This collective endeavor highlights the shared curiosity and ambition that drive scientific progress. Exploring whether the universe is infinite challenges our assumptions and encourages critical thinking. It pushes us to question what we know and remain open to new possibilities and discoveries. This question also has educational value, inspiring students and the public to engage with science and astronomy. It serves as a gateway to broader scientific literacy and appreciation for the complexities of the universe. Addressing the universe's size and nature can impact our worldview, affecting how we perceive our place in the cosmos and our relationship with the environment and each other. It fosters a sense of wonder and interconnectedness. The quest to determine the universe's infiniteness is a testament to human curiosity and our drive to understand the unknown. It exemplifies the spirit of exploration and the relentless pursuit of knowledge that defines humanity. Ultimately, the importance of this question lies in its ability to expand our horizons, challenge our intellect, and inspire awe. It connects us to the greater universe and the ongoing journey to unravel its mysteries. In this video, we'll embark on an exploration of one of the most profound questions in cosmology. Is the universe infinite? We'll begin with a look at historical perspectives, tracing how ancient civilizations and early scientists grappled with the concept of an infinite cosmos. Understanding these early ideas sets the stage for our modern inquiries. Next, we'll delve into the observable universe. We'll discuss what we can see with our current technology and the limitations of our observations. This section highlights the vastness of the cosmos within our observational reach. From there, we'll examine the cosmic microwave background radiation. We'll explore what this ancient light tells us about the early universe and its implications for the size and shape of the cosmos. Following that, we'll dive into the Big Bang theory. We'll outline the evidence supporting this theory and discuss what it means for the universe's expansion and potential infinity. Our journey will then take us into the realms of dark matter and dark energy. These mysterious components play crucial roles in the universe's behavior and could hold keys to understanding its ultimate fate. We'll explore the shape and geometry of the universe, considering whether it's flat, open, or closed. Each shape has different implications for the universe's potential infinity, and we'll examine the current evidence. The expansion of the universe is another critical topic. We'll discuss how we measure this expansion, what it tells us about the cosmos, and the role of dark energy in this process. We'll also venture into the intriguing idea of the multiverse. This theory suggests our universe might be one of many, raising fascinating questions about infinity and parallel realities. Philosophical and theoretical implications of an infinite universe will be another focal point. We'll delve into how infinity challenges our understanding of existence and the paradoxes it introduces. We'll then present the current scientific consensus on the universe's size. This section will highlight leading theories, key figures in modern cosmology, and ongoing debates. Our discussion will continue with an exploration of ongoing research and technological advancements. We'll look at how new discoveries could reshape our understanding of the cosmos and its limits. Predictions for future discoveries will follow, as we consider what upcoming missions and telescopes might reveal about the universe's true nature. We'll also reflect on personal perspectives, discussing how contemplating the universe's size and nature affects our worldview and sense of place in the cosmos. Throughout the video, we'll emphasize the importance of curiosity and the drive to explore. This journey through the cosmos is a testament to humanity's relentless pursuit of knowledge and understanding. Finally, we'll invite you to join us in this exploration, encouraging you to stay curious and engaged as we continue to unravel the mysteries of the universe. In ancient times, many cultures sought to explain the cosmos through myths and legends. These stories often depicted the universe as a finite space, enclosed and protected by gods or supernatural forces. The ancient Egyptians envisioned the sky as a goddess named Nut, arching over the earth and separating it from the chaotic waters of the cosmos. Their universe was a structured and ordered realm, maintained by divine beings. In Greek mythology, the universe began with chaos, a primordial void. From chaos emerged Gaia, the earth, and Uranus, the sky. This creation myth depicted the universe as a series of concentric spheres, with Earth at the center. The Norse mythology described a universe composed of 9 realms, all connected by the world tree, Yggdrasil. This cosmic structure was finite and cyclical, with worlds destined to end and be reborn in a perpetual cycle. Hindu cosmology presented a more complex view, with an infinite series of universes, each created and destroyed by the cycles of Brahma. This concept of endless creation and destruction introduced the idea of an infinite cosmos. In Chinese mythology, the universe was divided into the realms of heaven, earth, and the underworld. The cosmos was maintained by a balance of yin and yang, and the heavens were governed by the Jade Emperor. The ancient Mayans envisioned a layered universe with 13 heavens and 9 underworlds. Their cosmology included cyclical time, with the universe undergoing regular periods of creation and destruction. Mesopotamian beliefs described the universe as a flat disk enclosed by a dome, with the heavens above and the underworld below. This finite and ordered structure was maintained by a pantheon of gods. The Aztecs believed in a universe that had undergone multiple creations and destructions. Each cycle ended with a cataclysmic event, after which the gods would create a new world, suggesting an infinite series of universes. Indigenous Australian myths often depicted the universe as an interconnected web of land, sky, and spirit. These stories emphasized the eternal and cyclical nature of existence, reflecting an infinite and dynamic cosmos. Inuit mythology described a universe where the sky was a dome of hard material, with holes allowing light from the celestial realms to shine through. This finite view was balanced by a rich spiritual understanding of the cosmos. The ancient Persians, through Zoroastrian beliefs, saw the universe as a battleground between the forces of good and evil. This cosmic dualism implied a finite world that would eventually reach an ultimate resolution. Celtic mythology featured a universe with multiple worlds connected by mystical pathways. These other worlds were often accessible through sacred sites, suggesting a complex and layered cosmos. Japanese Shinto beliefs described a universe created by divine beings, with the heavens, earth, and underworld forming a balanced and interconnected whole. The cyclical nature of existence reflected an ongoing cosmic order. Native American myths varied widely, but often included elements of an interconnected and infinite cosmos, where the natural and spiritual worlds were closely linked. These stories emphasized harmony and balance within the universe. Philosophical debates about the nature of the universe have spanned centuries, delving into the concepts of infinity, existence, and reality. These discussions often reflect the intellectual currents of their times. The ancient Greeks were among the first to philosophize about the universe's infinity. Pythagoras and his followers believed in a cosmos that was both ordered and finite. In contrast, The atomists like Democritus argued for an infinite universe composed of indivisible atoms. Plato and Aristotle had differing views on the cosmos. Plato's ideas, rooted in ideal forms, suggested a finite universe reflecting these perfect forms. Aristotle, on the other hand, posited a finite but eternal universe, with the Earth at its center, surrounded by concentric celestial spheres. Medieval scholars, influenced by religious doctrines, often viewed the universe as finite and created by a divine being. However, the Islamic philosopher Al-Farabi and later thinkers like Thomas Aquinas incorporated Aristotelian ideas, blending them with theological concepts. In the Renaissance, Nicholas Copernicus challenged the geocentric view, proposing a heliocentric model that opened new philosophical debates about the universe's structure and extent. This shift laid the groundwork for modern cosmology. Giordano Bruno, a controversial figure, argued for an infinite universe with countless stars and possibly inhabited worlds. His ideas were radical and met with fierce opposition, but they influenced later thinkers who considered the vastness of space. The Enlightenment brought further philosophical inquiry into the nature of the universe. Immanuel Kant proposed the idea of island universes, suggesting that the Milky Way was just one of many galaxies, hinting at an infinite cosmos. David Hume's skepticism extended to the universe's infinity. He questioned the limits of human understanding and the ability to comprehend an infinite reality, highlighting the epistemological challenges in studying the cosmos. German philosopher Georg Wilhelm Friedrich Hegel saw the universe as a rational whole, with history and existence unfolding in a dialectical process. His ideas influenced subsequent philosophical debates about the nature of reality and the cosmos. Arthur Schopenhauer viewed the universe through a lens of metaphysical pessimism, suggesting that human perception shapes our understanding of reality. His work questioned the nature of existence and the possibility of an infinite cosmos. Existentialist philosophers like Jean-Paul Sartre and Albert Camus grappled with the absurdity of existence in a seemingly indifferent and possibly infinite universe. Their work reflects the existential angst of contemplating an infinite cosmos. The 20th century saw the rise of analytical philosophy, with thinkers like Ludwig Wittgenstein and Bertrand Russell examining the language and logic used to describe the universe. Their work underscores the complexities of discussing infinity. Contemporary philosophers continue to debate the implications of an infinite universe. Theoretical considerations from physics, such as the multiverse hypothesis, have revitalized philosophical discussions about the nature of reality and infinity. Philosophers also explore the ethical and existential implications of an infinite universe. Questions about human significance, purpose, and the moral framework of our actions gain new dimensions in the context of an endless cosmos. These ongoing debates illustrate the profound impact that the question of the universe's infinity has on our understanding of existence. As our scientific knowledge expands, so too does the philosophical inquiry into the nature of the cosmos, continuing a rich tradition of exploration and wonder. Early scientific theories about the universe marked the transition from mythological and philosophical speculation to empirical investigation and mathematical description. These theories laid the foundation for modern cosmology. Ptolemy's geocentric model, described in the Almagest, dominated for over a millennium. He proposed that the Earth was at the center of the universe, with planets and stars moving in complex orbits around it. This model, though flawed, explained the observed motions of celestial bodies fairly well. In the 16th century, Nicholas Copernicus revolutionized our understanding with his heliocentric theory. He proposed that the Sun, not the Earth, was at the center of the universe, with planets, including Earth, orbiting around it. This theory simplified the understanding of celestial motions and challenged long-held beliefs. Tycho Brahe, though supporting a hybrid model, made precise astronomical observations that were crucial for later advancements. His detailed records of planetary positions provided essential data for future theories. Johannes Kepler built on Brahe's data to formulate his laws of planetary motion. He discovered that planets orbit the Sun in elliptical paths, not perfect circles. Kepler's laws provided a more accurate description of planetary movements, supporting the heliocentric model. Galileo Galilei's telescopic observations offered direct evidence for the Copernican system. He discovered the moons of Jupiter, the phases of Venus, and the detailed surface of the Moon, all of which contradicted the geocentric model and supported a heliocentric universe. Isaac Newton's laws of motion and universal gravitation unified the understanding of celestial and terrestrial mechanics. His work explained the forces governing planetary orbits and established a framework for classical mechanics that dominated scientific thought for centuries. In the 18th and 19th centuries, the discovery of new planets and improved telescopes expanded our understanding of the solar system and the universe. William Herschel's discovery of Uranus and subsequent observations of nebulae hinted at the vastness of the cosmos beyond our solar system. The nebula hypothesis, proposed by Pierre-Simon Laplace, suggested that the solar system formed from a rotating cloud of gas and dust. This early theory of planetary formation introduced ideas about the origins of celestial bodies and the evolution of the cosmos. In the early 20th century, Edwin Hubble's observations led to the discovery of galaxies beyond the Milky Way. His work revealed that the universe was much larger than previously thought, and that it was expanding, leading to the formulation of the Big Bang theory. Albert Einstein's theory of general relativity provided a new framework for understanding gravity and the structure of space-time. His equations predicted an expanding or contracting universe, which was later confirmed by Hubble's observations. The development of quantum mechanics introduced new concepts about the fundamental nature of the universe. Theories by Max Planck, Niels Bohr, and others described the behavior of particles at the smallest scales, challenging classical notions of reality. The discovery of the cosmic microwave background radiation in the 1960s provided strong evidence for the Big Bang theory. This relic radiation from the early universe offered a snapshot of the cosmos shortly after its formation, supporting the idea of an expanding universe. The steady-state theory proposed by Fred Hoyle and others suggested that the universe had no beginning or end and was always expanding, with new matter continuously created. This theory competed with the Big Bang theory until the discovery of the cosmic microwave background radiation. These early scientific theories and discoveries transformed our understanding of the universe from a finite geocentric system to an expanding dynamic cosmos. They set the stage for contemporary cosmology and the ongoing quest to determine whether the universe is infinite. Religion has profoundly shaped humanity's understanding of the universe, influencing beliefs about its origin, structure, and fate. Different religious traditions offer diverse perspectives on whether the universe is finite or infinite. In Christianity, the concept of creation ex nihilo, or creation from nothing, suggests a finite universe created by an omnipotent God. The Bible describes a beginning and an end, framing the universe within a linear timeline. Islamic cosmology also portrays a universe created by a singular, all-powerful God. The Quran describes the heavens and the earth as a divine creation, emphasizing the universe's order and purpose within a finite framework. Hinduism presents a more cyclical view of the cosmos. The concept of infinite cycles of creation, preservation, and destruction by deities like Brahma, Vishnu, and Shiva implies an eternally regenerating universe, blending both finite and infinite elements. Buddhism offers a cosmology where the universe undergoes endless cycles of formation and dissolution. This perspective aligns with the idea of a potentially infinite cosmos, with no ultimate beginning or end. Ancient Greek religion influenced early scientific thought with its pantheon of gods associated with celestial bodies. Myths involving gods like Zeus and Apollo intertwined with early astronomical theories, impacting perceptions of the universe's nature. In Norse mythology, the cosmos is depicted as a finite yet cyclical realm, with Yggdrasil, the world tree, connecting different worlds. The eventual destruction and rebirth during Ragnarok reflect an ongoing cosmic cycle. Native American spiritual beliefs often emphasize the interconnectedness of all things within the universe. These traditions view the cosmos as a living entity, with no clear beginning or end, suggesting an infinite dynamic existence. Indigenous Australian Dreamtime stories describe the creation of the world by ancestral spirits. These narratives often portray a timeless and interconnected universe, blending elements of the finite and infinite. Chinese religious traditions, including Taoism and Confucianism, emphasize harmony within the universe. The Taoist concept of the Tao as an eternal and infinite principle governing the cosmos suggests a boundless universe. Judaism presents a cosmology where the universe is created by God, with a clear beginning as described in Genesis. The finite nature of creation is balanced by the infinite nature of God, intertwining temporal and eternal elements. Zoroastrianism introduces a dualistic view of the cosmos, with a constant struggle between good and evil forces. This battle occurs within a finite universe, destined to be purified and renewed, leading to an ultimate resolution. In Jainism, the universe is eternal and uncreated, composed of cycles of rise and fall. This belief system views the cosmos as infinite in both space and time, without a beginning or an end. Sikhism describes the universe as created by one God, with a finite beginning but an infinite nature reflecting the eternal nature of the divine. This blend of finite creation and infinite existence reflects a unique cosmological perspective. Mayan cosmology envisioned the universe as a structured, layered realm, governed by cycles of time. The constant creation and destruction within these cycles suggest a dynamic, potentially infinite cosmos. These religious perspectives have significantly influenced human thought about the universe, blending finite and infinite elements in diverse ways. They provide a rich tapestry of beliefs that continue to shape our understanding and inspire our quest for knowledge. To understand if the universe is infinite, we need to define what we mean by the universe and its scope. The universe encompasses all of space, time, matter, and energy. It includes everything from the smallest subatomic particles to the largest galaxies. When we talk about the observable universe, we refer to the portion we can see or detect with our instruments. This is limited by the speed of light and the age of the universe, roughly 13.8 billion years. Beyond this observable limit, there could be much more that we cannot see. The concept of the universe also includes the idea of SpaceTime, the four-dimensional continuum where all events occur. SpaceTime combines three spatial dimensions with one time dimension, forming the fabric of the cosmos. In defining the universe, we must consider the laws of physics that govern it. These laws, including gravity, electromagnetism, and quantum mechanics, provide a framework for understanding how the universe behaves and evolves. The scope of the universe involves vast scales of distance and time. On the larger scales, it is structured into clusters and superclusters of galaxies, interconnected by dark matter and separated by vast voids. We also consider the universe's scope in terms of its contents. It includes ordinary matter, and dark energy. Ordinary matter makes up a small fraction of the total mass-energy content, while dark matter and dark energy dominate. Dark matter does not emit or absorb light, making it invisible to us. We infer its existence from its gravitational effects on visible matter, such as galaxies and clusters of galaxies. Dark energy is a mysterious force driving the accelerated expansion of the universe. It makes up about 68% of the universe's total energy density and remains one of the biggest puzzles in cosmology. The definition and scope of the universe also involve understanding its origin and evolution. The Big Bang Theory describes the universe's beginning as a hot, dense state that has been expanding and cooling over time. As the universe expands, it stretches the fabric of space-time, causing galaxies to move away from each other. This expansion is measured by the redshift of light from distant galaxies, which increases with distance. We also explore the possibility of a multiverse, where our universe is just one of many. This concept extends the scope of what we consider the universe to include multiple, possibly infinite, parallel universes. The scope of the universe includes its potential shape and geometry. Current evidence suggests it is flat on large scales, but it could also be open or closed. Each shape has different implications for its size and future. To fully grasp the scope of the universe, we also consider its possible fate. Theories range from a continuous expansion leading to a cold, dark universe, to a big crunch where it collapses back on itself, or a big rip where dark energy tears everything apart. Understanding the universe's scope involves continuous exploration and observation. Advances in technology such as telescopes and satellites enable us to see further and more clearly, expanding our knowledge of the cosmos. In defining and exploring the scope of the universe, we aim to answer fundamental questions about its nature, origin, and ultimate destiny. This journey of discovery continues to push the boundaries of our understanding and inspire awe at the vastness of the cosmos. Observing the universe requires advanced technology and innovative methods. Telescopes are our primary tools, and they come in various types, each suited for different observations. Optical telescopes capture visible light, allowing us to see stars, galaxies, and other celestial objects. They range from small amateur telescopes to large observatories, like the Hubble Space Telescope. Radio telescopes detect radio waves emitted by objects in space. These telescopes reveal phenomena such as pulsars, quasars, and the cosmic microwave background radiation. Infrared telescopes observe heat emitted by celestial bodies. They can see through dust clouds that obscure visible light, revealing star formation regions and the structure of galaxies. X-ray telescopes detect high-energy radiation from sources like black holes, neutron stars, and supernova remnants. These observations help us understand extreme conditions and energetic processes in the universe. Space-based telescopes avoid the distortions caused by Earth's atmosphere. Instruments like the James Webb Space Telescope provide clearer and more detailed views of the cosmos. Ground-based observatories benefit from adaptive optics, which correct for atmospheric turbulence in real time, improving image quality. Examples include the Very Large Telescope and the Keck Observatory. Spectroscopy is a key method for analyzing light from celestial objects. By spreading light into its component colors, we can determine the composition, temperature, and motion of stars and galaxies. Gravitational wave detectors, like LIGO and Virgo, observe ripples in spacetime caused by violent events, such as merging black holes or neutron stars. These observations open a new window into the universe. Particle detectors, such as those used in neutrino observatories, detect elusive particles from cosmic sources. These particles provide information about processes occurring in distant stars and galaxies. Surveys and catalogues compile extensive data on millions of celestial objects. Projects like the Sloan Digital Sky Survey map large portions of the sky, providing valuable resources for astronomers. Robotic spacecraft and probes like the Voyager missions explore the solar system and beyond, sending back detailed images and measurements from distant worlds. Astrometry measures the precise positions and movements of stars. This method helps us understand stellar dynamics and detect exoplanets by observing the tiny wobbles they cause in their parent stars. Photometry measures the brightness of celestial objects over time. This technique is essential for studying variable stars, detecting exoplanets, and observing supernovae. Computer simulations model the universe's behavior based on physical laws and observed data. These simulations help us test theories and predict phenomena that we can compare with actual observations. Citizen science projects engage the public in data analysis, expanding the capacity for discovery. Volunteers help identify celestial objects and phenomena, contributing to scientific research. These diverse methods of observation work together to provide a comprehensive understanding of the universe. Each method reveals different aspects of the cosmos, contributing to our ongoing quest to uncover its mysteries. Despite our advanced technology, there are significant limits to what we can observe in the universe. These limitations often shape our understanding and drive the development of new technologies. One major limitation is the speed of light. Because light takes time to travel, we can only see objects as they were in the past. The farther away an object is, the older the light we receive, meaning we look back in time but cannot see the present state of distant objects. Telescopes, both ground-based and space-based, have resolution limits. The clarity and detail of images depend on the size of the telescope's mirror or lens and the quality of its instruments. Even the largest telescopes can only see so much detail. Atmospheric interference is another challenge for ground-based observatories. The Earth's atmosphere can distort and absorb light, making it difficult to obtain clear images. Adaptive optics can mitigate this, but only to a certain extent. Space telescopes avoid atmospheric issues but face other challenges, such as limited size and lifespan. Launching large telescopes into space is expensive and complex, and once there, they are difficult to repair or upgrade. Radio telescopes, while powerful, have limited resolution compared to optical telescopes. Interferometry, which combines signals from multiple radio telescopes, can improve resolution but requires precise coordination and extensive infrastructure. Infrared observations are hampered by the heat emitted by the Earth and the telescopes themselves. Cooling the instruments to very low temperatures is necessary, but technologically demanding and expensive. X-ray and gamma-ray telescopes face difficulties in detecting high-energy photons, which require specialized detectors and shielding to block background radiation. These telescopes also need to be placed in space to avoid atmospheric absorption. Gravitational wave detectors are limited by their sensitivity to tiny distortions in space-time. Current detectors can only observe the most powerful events, such as black hole mergers, and are affected by ground vibrations and noise. Particle detectors rely on rare interactions between particles and detectors, requiring large volumes and long observation times. Neutrino detectors, for example, need vast amounts of water or ice to catch these elusive particles. Astrometry, which measures star positions and movements, is limited by the precision of instruments and the time required to detect changes. Small movements over vast distances need extremely accurate measurements. Photometry, which measures changes in brightness, can be affected by atmospheric conditions and instrumental noise. Detecting minute variations, such as those caused by exoplanets, requires highly sensitive instruments and stable observation conditions. Surveys and catalogues are limited by the sheer volume of data. Processing and analyzing data from millions of objects is computationally intensive, and even with automated systems, some details can be overlooked. Computer simulations of the universe are constrained by the power of current supercomputers and the accuracy of the models. Simulating the entire universe at high resolution requires immense computational resources and can only approximate reality. Robotic spacecraft and probes are limited by their power sources, communication delays, and the harsh conditions of space. Missions take years to reach distant targets, and instruments can degrade over time. Citizen science projects, while valuable, rely on the participation and accuracy of non-professional volunteers. Ensuring consistent and reliable results from diverse contributors can be challenging. These limits highlight the need for continual technological innovation and collaboration. Each advancement brings us closer to understanding the universe, pushing the boundaries of what we can observe and comprehend. The observable universe is the portion of the entire universe that we can see or detect from Earth. It spans about 93 billion light-years in diameter, limited by the age of the universe and the speed of light. Beyond the observable universe lies the total universe, which may be vastly larger and more complex. We cannot see or measure these distant regions directly, but we infer their existence from cosmological models and theories. The difference between the observable and total universe arises because light from beyond the observable universe has not had enough time to reach us. As the universe expands, regions beyond our observable limit continue to recede. Our understanding of the observable universe comes from various observations, including the cosmic microwave background radiation, which provides a snapshot of the early universe. This radiation helps us infer properties of the universe beyond what we can directly observe. While the observable universe contains billions of galaxies, the total universe could contain many more, possibly an infinite number. This raises questions about the true scale and nature of the cosmos. In the observable universe, we see a homogeneous and isotropic structure on large scales, meaning it appears similar in all directions. If the total universe extends far beyond, this homogeneity might continue, or it could vary in ways we cannot predict. The concept of the total universe includes regions that may never be observable due to the universe's accelerated expansion, driven by dark energy. These regions are beyond our causal reach, meaning we cannot interact with or receive information from them. The total universe might also encompass different physical laws or constants in various regions. Some theories suggest that other parts of the universe could have different properties, leading to a multiverse scenario. Understanding the distinction between the observable and total universe helps frame our quest for knowledge. While we gather data and develop models within our observable limits, we remain aware that much lies beyond our direct grasp. Cosmologists use indirect methods, such as studying cosmic inflation and the distribution of matter, to infer properties of the total universe. These methods help build a more comprehensive picture of the cosmos. The observable universe provides a laboratory for testing theories about the total universe. By comparing observations with predictions from various models, scientists refine their understanding of the broader cosmos. One challenge in studying the total universe is the horizon problem, where regions of the universe appear uniform despite being causally disconnected. This paradox suggests the need for a theory like cosmic inflation to explain such large-scale uniformity. Gravitational waves and other cosmic signals may offer new ways to probe beyond the observable universe. As detection methods improve, we might gain indirect evidence of what lies beyond our current observational limits. The relationship between the observable and total universe also touches on fundamental questions about infinity and the nature of reality. If the total universe is infinite, it raises profound philosophical and scientific questions about its origin and structure. As we continue to explore the observable universe, we push the boundaries of our knowledge, constantly seeking to understand the larger total universe. Each discovery brings us a step closer to comprehending the full extent of the cosmos. This journey highlights the interplay between observation and theory in cosmology. While our view is limited, our curiosity and ingenuity drive us to explore and imagine the vastness that lies beyond. One of the most significant discoveries in cosmology is the expansion of the universe. Edwin Hubble observed that galaxies are moving away from us, with their light redshifted, indicating an expanding cosmos. The discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson provided crucial evidence for the Big Bang theory. This faint glow is the afterglow of the universe's hot, dense origin. The observation of dark matter revolutionized our understanding of the universe's composition. Fritz Zwicky first noticed missing mass in galaxy clusters, leading to the concept of unseen matter that exerts gravitational effects. Vera Rubin's work on galaxy rotation curves further confirmed the presence of dark matter. She found that stars in galaxies rotated at speeds suggesting more mass than what was visible, supporting the dark matter hypothesis. The discovery of dark energy, which drives the accelerated expansion of the universe, was another groundbreaking finding. Observations of distant supernovae revealed this mysterious force, altering our understanding of cosmic dynamics. The detailed mapping of the cosmic microwave background by missions like COBE, WMAP, and Planck has provided a wealth of information about the universe's early conditions, composition, and structure. The detection of gravitational waves by LIGO opened a new window for observing the universe. These ripples in spacetime, caused by violent events like black hole mergers, confirm predictions of Einstein's general relativity. Exoplanet discoveries have expanded our knowledge of planetary systems beyond our own. The Kepler Space Telescope and other missions have identified thousands of exoplanets, some potentially habitable, orbiting distant stars. The measurement of the Hubble constant, which describes the universe's expansion rate, has been refined through various methods, including observations of the cosmic microwave background and distant supernova. The discovery of the Higgs boson at CERN confirmed the existence of the Higgs field, which gives particles mass. This finding supports the Standard Model of particle physics, a key framework for understanding fundamental forces. Mapping the large-scale structure of the universe has revealed the cosmic web, a vast network of galaxies and dark matter. Surveys like the Sloan Digital Sky Survey have shown how galaxies cluster and distribute on enormous scales. The study of cosmic inflation, a rapid expansion of the universe shortly after the Big Bang, has been supported by observations of the cosmic microwave background and large-scale structure, providing insights into the universe's early moments. The identification of cosmic neutrinos by detectors like IceCube has given us a new way to study high-energy processes in the universe. These elusive particles travel vast distances, carrying information from their sources. The discovery of fast radio bursts, intense bursts of radio waves from distant galaxies, has puzzled astronomers and opened a new area of research. Understanding their origins could reveal new astrophysical phenomena. The use of adaptive optics in ground-based telescopes has significantly improved our ability to observe celestial objects with greater clarity. This technology corrects for atmospheric distortions, bringing us clearer images of distant stars and galaxies. These key discoveries have transformed our understanding of the universe, each contributing to the intricate puzzle of cosmology. They illustrate the power of human curiosity and ingenuity in unraveling the mysteries of the cosmos. The cosmic microwave background, or CMB, is the faint glow of radiation left over from the early universe. It provides a snapshot of the cosmos when it was just 380,000 years old, a time known as the recombination era. During recombination, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This allowed light to travel freely for the first time, creating the CMB. The CMB is incredibly uniform, but it has tiny temperature fluctuations. These fluctuations, observed as slight differences in the intensity of the CMB, correspond to density variations in the early universe. These density variations eventually led to the formation of galaxies and large-scale structures. By studying the CMB, scientists can learn about the conditions of the early universe and the processes that shaped its evolution. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, the CMB was a pivotal finding. It provided strong evidence for the Big Bang theory, confirming that the universe began in a hot, dense state. The CMB is now observed using advanced space telescopes like COBE, WMAP, and Planck. These missions have mapped the CMB with high precision, revealing detailed information about the universe's early moments. The temperature of the CMB is about 2.7 Kelvin, just above absolute zero. This uniform temperature supports the idea that the universe was once in thermal equilibrium before it expanded and cooled. Tiny fluctuations in the CMB's temperature, about 1 part in 100,000, carry important information. These anisotropies provide clues about the universe's composition, age, and rate of expansion. The CMB also shows evidence of the universe's large-scale geometry. Observations suggest that the universe is flat, meaning its geometry conforms to Euclidean principles on large scales. By analyzing the CMB, scientists can estimate the universe's age. Current measurements place the age at approximately 13.8 billion years, based on the time it took for the observed fluctuations to develop. The polarization of the CMB offers additional insights. It reveals the impact of gravitational waves from the early universe, shedding light on the epoch of inflation that occurred moments after the Big Bang. The CMB acts as a cosmic backlight, illuminating the structure and distribution of matter in the universe. Its study helps cosmologists understand dark matter, dark energy, and the overall dynamics of cosmic evolution. The CMB also provides constraints on fundamental constants of nature, such as the Hubble constant and the density parameters of different components of the universe. These constraints refine our cosmological models. Anomalies in the CMB, such as the cold spot, have sparked debates and further investigations. These features may hint at new physics or unusual cosmic events, pushing the boundaries of our understanding. The study of the CMB continues to be a cornerstone of cosmology. It remains a crucial tool for probing the universe's earliest moments, offering a window into the birth and evolution of the cosmos. The CMB's discovery and detailed analysis have revolutionized our view of the universe, turning the night sky into a cosmic archive of its most ancient secrets. The discovery of the cosmic microwave background was a monumental event in cosmology. It provided the first direct evidence supporting the Big Bang theory, transforming our understanding of the universe's origins. In 1965, Arno Penzias and Robert Wilson were working with a radio antenna at Bell Labs. They encountered persistent noise that they couldn't explain, which turned out to be the CMB, a discovery that earned them the Nobel Prize in Physics. This accidental discovery confirmed predictions made by theoretical physicists years earlier. It validated the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. The significance of the CMB lies in its ability to offer a snapshot of the universe when it was just 380,000 years old. This ancient light provides a wealth of information about the early conditions of the cosmos. The uniformity of the CMB across the sky was one of its most striking features. This uniformity indicated that the universe was once in a state of thermal equilibrium before structures like galaxies began to form. Tiny temperature fluctuations in the CMB, or anisotropies, are crucial for understanding how the universe evolved. These fluctuations represent density variations that eventually led to the formation of galaxies and large-scale structures. Detailed measurements of these anisotropies by missions like COBE, WMAP, and Planck have provided precise data on the universe's composition, age, and rate of expansion. This data has been essential for refining cosmological models. The CMB also offers insights into the geometry of the universe. Observations suggest that the universe is flat, which has profound implications for its overall structure and future evolution. Polarization of the CMB provides additional information about the early universe. It can reveal the influence of gravitational waves from the inflationary period, offering clues about the universe's first moments. The CMB helps us understand the relative amounts of ordinary matter, and dark energy. By analyzing the CMB, scientists can estimate these components' densities and their roles in cosmic evolution. The discovery of the CMB also helped resolve competing theories about the universe's origin. It strongly supported the Big Bang model over the steady-state theory, which posited a continuous creation of matter. Anomalies in the CMB, such as the cold spot, have intrigued scientists and sparked debates. These features may indicate new physics or unusual cosmic events, pushing researchers to explore beyond current models. The study of the CMB has driven technological advancements in observational astronomy. The development of sensitive instruments and sophisticated data analysis techniques has enhanced our ability to probe the universe. The CMB acts as a cosmic backlight, illuminating the large-scale structure of the universe. Its study helps cosmologists map the distribution of matter and understand the formation and evolution of cosmic structures. Overall, the discovery and study of the CMB have been pivotal in shaping modern cosmology. This ancient light continues to be a key source of information about the universe's earliest moments, guiding our quest to understand the cosmos. The cosmic microwave background, or CMB, provides a wealth of information about the early universe. By studying the CMB, we can learn about the universe's age, composition, and evolution. The uniformity of the CMB tells us that the early universe was in a state of thermal equilibrium. This uniformity suggests that the universe started from a hot, dense state and expanded uniformly over time. The tiny temperature fluctuations in the CMB are crucial for understanding the formation of cosmic structures. These fluctuations represent slight differences in density, which acted as seeds for the formation of galaxies and clusters. By analyzing the CMB, scientists can determine the universe's age with great precision. Current measurements indicate that the universe is approximately 13.8 billion years old. The CMB also provides information about the composition of the universe. It reveals the relative amounts of ordinary matter, and dark energy, helping us understand their roles in cosmic evolution. The polarization of the CMB gives us clues about the universe's early moments, particularly the period of inflation. Inflation was a rapid expansion that occurred fractions of a second after the Big Bang, smoothing out any initial irregularities. Observations of the CMB support the theory that the universe is flat. This flatness means that the geometry of the universe conforms to Euclidean principles, which has implications for its overall structure and fate. The CMB helps us understand the rate of the universe's expansion. By studying the redshift of light and the distribution of galaxies, we can measure how quickly the universe has been expanding since the Big Bang. Detailed maps of the CMB, such as those produced by the Planck satellite, show the distribution of temperature fluctuations across the sky. These maps help us trace the large-scale structure of the universe and its evolution over time. The CMB acts as a cosmic backlight, illuminating the dark matter that makes up a significant portion of the universe. By studying how the CMB's light is bent by gravitational lenses, we can map the distribution of dark matter. The CMB also provides insights into the physics of the early universe. It helps us test theories about fundamental forces and particles, including those that governed the universe during its first moments. Anomalies in the CMB, like the cold spot, suggest there may be more to learn about the universe's history and structure. These features challenge existing models and inspire new theories and observations. The CMB's tiny fluctuations help cosmologists understand the initial conditions of the universe. These conditions set the stage for all subsequent cosmic evolution, from the formation of atoms to the development of galaxies. The study of the CMB has driven advancements in both theory and technology. Instruments designed to measure the CMB have led to innovations in data analysis, detector technology, and observational techniques. Overall, the CMB is a cornerstone of modern cosmology. It provides a snapshot of the universe at a young age, offering invaluable insights into its origin, composition, and evolution. This ancient light continues to guide our understanding of the cosmos, revealing the secrets of the universe's earliest moments. The study of the cosmic microwave background has significant implications for understanding the size of the universe. By analyzing the CMB, scientists gain insights into the overall scale and extent of the cosmos. The uniformity of the CMB across the sky suggests that the observable universe is just a small part of a much larger whole. This implies that the universe could be far more extensive than what we can currently observe. Tiny fluctuations in the CMB provide clues about the universe's geometry. Observations indicate that the universe is flat, suggesting it could be infinite in size. A flat universe aligns with the concept of an infinite expanse. The detailed maps of the CMB created by satellites like Planck reveal the distribution of matter and energy in the universe. These maps help us understand the large-scale structure, indicating a vast, interconnected web of galaxies and dark matter. The CMB also informs us about the rate of expansion of the universe. By measuring this rate, scientists can infer the size of the universe at different points in its history, helping to estimate its overall size and growth. The concept of cosmic inflation, supported by CMB observations, suggests that the universe underwent a rapid expansion shortly after the Big Bang. This inflationary period would have stretched the universe to an enormous size, possibly making it infinite. The temperature fluctuations in the CMB indicate regions of varying density in the early universe. These density variations led to the formation of large-scale structures, implying a universe that extends far beyond our observational limits. The study of the CMB also helps us understand the distribution of dark matter and dark energy. These components play crucial roles in the universe's expansion and structure, influencing its overall size and dynamics. Gravitational lensing of the CMB, where light is bent by massive objects, provides additional information about the distribution of matter in the universe. This effect helps map out regions that contribute to the universe's vastness. By comparing the CMB data with other cosmological observations, such as the distribution of galaxies and supernovae, scientists can create more accurate models of the universe's size and scale. The CMB's polarization patterns give insights into the early universe's conditions, which in turn affect our understanding of its size. These patterns help refine models of cosmic inflation and expansion. The discovery of the CMB and its subsequent study have reinforced the idea that the universe is much larger than previously thought. This realization has profound implications for cosmology and our place in the cosmos. The possibility of a multiverse, suggested by some interpretations of CMB data, extends the implications even further. If multiple universes exist, the size of our universe could be just one part of an even larger reality. Understanding the size of the universe helps address fundamental questions about its origin and fate. The CMB provides critical evidence for these inquiries, guiding theories about whether the universe is finite or infinite. Overall, the study of the CMB has transformed our understanding of the universe's size. It reveals a cosmos that is vast, complex, and possibly infinite, expanding our horizons and challenging our perceptions of the universe's true scale. Ongoing research into the cosmic microwave background continues to refine our understanding of the universe. Scientists use increasingly sophisticated tools and methods to probe deeper into the cosmos. Current missions, like the Planck satellite, have provided high-precision measurements of the CMB. These data help improve our models of the universe's early conditions and its subsequent evolution. Future missions are being planned to further investigate the CMB. These missions aim to provide even more detailed maps of the temperature fluctuations and polarization patterns. One area of focus is the study of primordial gravitational waves. These waves, predicted by inflation theory, leave imprints on the CMB's polarization, offering clues about the universe's earliest moments. Researchers are also looking at the integrated Sachs-Wolf effect, where the CMB interacts with large-scale structures in the universe. This effect helps measure dark energy's influence on cosmic expansion. Improving our understanding of cosmic inflation remains a key goal. By analyzing the CMB, scientists hope to test different inflationary models and determine which best describes the universe's rapid early expansion. The search for anomalies in the CMB, such as the cold spot, continues. These features might indicate new physics or unusual cosmic events, prompting further investigation and theoretical work. Cross-referencing CMB data with other cosmological observations enhances our knowledge. Combining CMB insights with data from galaxy surveys, gravitational waves, and other sources helps build a comprehensive picture of the universe. Advancements in data analysis techniques are crucial for ongoing research. Machine learning and artificial intelligence are being applied to CMB data to uncover patterns and extract more information. Collaboration between international research teams drives progress. Projects like the South Pole Telescope and the Atacama Cosmology Telescope involve scientists from around the world working together to study the CMB. New instruments and technologies are being developed to improve CMB measurements. These innovations aim to reduce noise and increase the sensitivity of observations, leading to more precise data. Theoretical research complements observational efforts. Scientists develop and refine models based on CMB data, exploring the implications for fundamental physics and cosmology. Public engagement and citizen science projects contribute to ongoing research. Amateur astronomers and volunteers help analyze data and identify features in the CMB, supporting professional efforts. Funding and support from government agencies and scientific organizations are essential. Continued investment in cosmology ensures that research into the CMB and the universe's origins can advance. The study of the CMB remains a dynamic field, with each discovery leading to new questions and directions for research. As technology improves and new data are collected, our understanding of the universe continues to evolve. Ongoing research into the CMB promises to uncover more about the cosmos's mysteries, pushing the boundaries of our knowledge and deepening our comprehension of the universe's origins and structure. The theory of the cosmic microwave background originates from the Big Bang model. It posits that the universe began as a hot, dense singularity about 13.8 billion years ago and has been expanding ever since. As the universe expanded, it cooled. About 380,000 years after the Big Bang, it cooled enough for protons and electrons to combine into hydrogen atoms, allowing photons to travel freely. This period is known as recombination. The radiation released during recombination is what we now detect as the cosmic microwave background. These photons have traveled through space for billions of years, stretching into the microwave range as the universe expands. The uniformity of the CMB supports the idea that the early universe was in thermal equilibrium. Tiny fluctuations in its temperature reflect minute density variations that grew into the large-scale structures we see today. Cosmic inflation theory, a rapid expansion of the universe fractions of a second after the Big Bang, explains the uniformity and flatness of the CMB. Inflation smoothed out any initial irregularities and stretched the universe to vast scales. Inflation also predicts the tiny quantum fluctuations that became the seeds for cosmic structures. These fluctuations are imprinted on the CMB as slight temperature variations, providing a snapshot of the universe's infancy. The theory also incorporates the effects of dark matter and dark energy. Dark matter influences the growth of structures in the universe, while dark energy drives its accelerated expansion, both detectable through the CMB. The Sachs-Wolf effect describes how large-scale structures affect the CMB. Photons from the CMB gain or lose energy as they pass through gravitational potentials, providing clues about the universe's expansion and structure. The theory explains the anisotropies, or small variations, in the CMB's temperature. These anisotropies are crucial for understanding the distribution of matter and energy in the early universe. The polarization of the CMB, predicted by the theory, results from Thomson scattering during recombination. This polarization pattern carries information about the conditions and processes in the early universe. The theory accounts for the integrated Sachs-Wolf effect, where the CMB interacts with evolving gravitational potentials. This effect helps measure the universe's expansion rate and dark energy's influence. Acoustic peaks in the CMB's power spectrum result from sound waves in the early universe's plasma. These peaks provide detailed information about the universe's composition, geometry, and expansion history. The theory includes the lensing of the CMB, where its path is bent by massive objects. This lensing effect helps map the distribution of dark matter and refine our understanding of the universe's large-scale structure. Gravitational waves predicted by inflation theory should leave faint imprints on the CMB's polarization. Detecting these imprints would provide direct evidence for inflation and further validate the Big Bang model. The cosmic microwave background theory, supported by extensive observational evidence, forms a cornerstone of modern cosmology. It connects the universe's earliest moments to its current structure, offering profound insights into the nature and origin of the cosmos. Evidence supporting the Big Bang theory is extensive and multifaceted, encompassing a range of observations and discoveries. One of the most compelling pieces of evidence is the cosmic microwave background itself. This ancient light is a relic from the early universe, providing a direct snapshot of the cosmos shortly after the Big Bang. The abundance of light elements such as hydrogen, helium, and lithium also supports the Big Bang theory. Observations show that the proportions of these elements match predictions from Big Bang nucleosynthesis, the process that occurred in the first few minutes after the Big Bang. Hubble's law provides another critical piece of evidence. Edwin Hubble discovered that galaxies are moving away from us, with their speed proportional to their distance. This observation indicates that the universe is expanding, a key prediction of the Big Bang theory. The large-scale structure of the universe observed through galaxy surveys aligns with predictions from the Big Bang model. The distribution of galaxies and clusters reflects the growth of initial density fluctuations, as seen in the cosmic microwave background. Observations of distant galaxies and quasars show that the universe has evolved over time. The light from these objects, which has traveled for billions of years, reveals changes in the universe's structure and composition, consistent with an expanding universe that began in a hot, dense state. The isotropy and homogeneity of the universe on large scales, as revealed by the cosmic microwave background, support the Big Bang theory. These characteristics suggest that the universe was once in a state of thermal equilibrium, a condition that the Big Bang model naturally explains. The discovery of dark energy and the accelerated expansion of the universe further corroborate the Big Bang theory. Observations of type Ia supernovae indicate that the universe's expansion is speeding up, a phenomenon that fits within the Big Bang framework when dark energy is included. The relationship between the age of the universe and the oldest known objects provides additional evidence. The age of globular clusters and white dwarf stars is consistent with the estimated age of the universe, derived from the cosmic microwave background and Hubble's law. Baryon acoustic oscillations, or BAOs, are regular, periodic fluctuations in the density of visible matter. These oscillations, observed in the large-scale structure of the universe, match predictions from the early universe's sound waves, providing further support for the Big Bang model. Gravitational lensing, the bending of light by massive objects, reveals the distribution of dark matter. This distribution, inferred from lensing patterns, matches the structures predicted by simulations based on the Big Bang theory. The discovery of the Higgs boson at CERN's Large Hadron Collider confirms the existence of the Higgs field, a crucial component of the standard model of particle physics. This model integrates seamlessly with the Big Bang theory, explaining how particles acquired mass in the early universe. The cosmic neutrino background, though not yet directly observed, is another predicted relic of the Big Bang. Indirect evidence from particle physics experiments supports its existence, adding another layer to the Big Bang's predictive power. Gamma-ray background radiation, detected by various space telescopes, includes contributions from processes occurring in the early universe. This radiation fits the expected patterns from the Big Bang's high-energy processes. The polarization of the cosmic microwave background, observed by missions like Planck, contains signatures of primordial gravitational waves. These waves are a predicted consequence of cosmic inflation, an early phase of the Big Bang, providing indirect evidence for the theory. Combined, these pieces of evidence form a robust foundation for the Big Bang theory. Each observation not only supports the model but also enhances our understanding of the universe's origins, composition, and evolution. This comprehensive body of evidence underscores the Big Bang as the leading explanation for the birth and development of the cosmos. Many people mistakenly believe the Big Bang was an explosion in space. In reality, it was an expansion of space itself, happening everywhere at once, not from a single point. Another common misconception is that the Big Bang provides an explanation for the origin of the universe. It actually describes the development of the universe from an extremely hot and dense state, not the ultimate origin of all matter and energy. Some think the Big Bang theory is just a speculative idea without evidence. However, it's supported by extensive observations, including the cosmic microwave background, the distribution of galaxies, and the abundance of light elements. A frequent misunderstanding is that the universe is expanding into pre-existing space. Instead, space itself is expanding, meaning distances between objects in the universe are increasing. People often imagine the universe as having a center from which everything expands. The Big Bang theory indicates that the expansion occurs uniformly, with no central point, similar to how the surface of a balloon expands. It's a misconception that galaxies themselves are expanding. The galaxies remain intact while the space between them expands, causing them to move away from each other. Some believe the Big Bang contradicts the laws of physics, but the theory is built on well-established principles of physics and has been refined to align with observed data. There's a notion that the Big Bang implies the universe must have started from a singularity. While the concept of a singularity is a feature of general relativity, quantum theories suggest the conditions at the very beginning may differ. Many think the Big Bang was the beginning of time. While it marks the start of the observable universe, the nature of time before the Big Bang is still a topic of theoretical research and debate. A common myth is that the Big Bang was loud. Since sound cannot travel through the vacuum of space, there was no sound as we understand it. Some assume that the universe's expansion should slow down over time. Observations show that the expansion is accelerating due to dark energy, which was a surprising discovery for cosmologists. It's often thought that the Big Bang happened billions of years ago, and nothing can be known about it. However, the cosmic microwave background allows us to observe the universe as it was just 380,000 years after the Big Bang. Another misconception is that the Big Bang theory is incompatible with religious beliefs. In reality, many people find ways to reconcile their faith with scientific understandings of the universe. Some think that if the Big Bang theory changes, it means the theory is wrong. Science constantly evolves with new evidence, refining and improving theories to better describe the natural world. Lastly, people often confuse the Big Bang theory with the steady-state theory. The steady-state theory posits a constant universe without beginning or end, while the Big Bang theory describes a dynamic, evolving cosmos. The Big Bang theory significantly influences our understanding of the universe's size. According to the theory, the universe has been expanding since its inception about 13.8 billion years ago. This expansion means that the distances between galaxies are increasing over time. The further away a galaxy is, the faster it appears to be moving away from us, suggesting a continually growing universe. One way to measure the universe's size is by looking at the cosmic microwave background. This ancient light provides a snapshot of the early universe, helping us estimate its current scale and structure. The Hubble constant, which measures the rate of expansion, is crucial for determining the universe's size. By understanding how quickly the universe is expanding, scientists can infer its overall dimensions. The discovery of dark energy, which accelerates the universe's expansion, implies that the universe will continue to grow indefinitely. This ongoing expansion affects our estimates of the universe's size. The concept of the observable universe is tied to the Big Bang theory. It refers to the region of space from which light has had time to reach us since the Big Bang, roughly 93 billion light-years in diameter. Beyond the observable universe lies the unobservable universe, which might be vastly larger. The Big Bang theory suggests that regions far beyond our observational limits exist, expanding the potential size of the cosmos. Inflation theory, an extension of the Big Bang, proposes a rapid expansion immediately after the universe's birth. This inflationary period stretched the universe to an enormous size very quickly, potentially making it infinite. The distribution of galaxies and cosmic structures provides clues about the universe's size. Observations show that galaxies form a web-like structure, extending as far as we can see and suggesting a vast, interconnected universe. Gravitational lensing, where massive objects bend light, helps map the universe's structure. By studying these lensing effects, scientists can infer the presence of dark matter and further understand the universe's vastness. The Big Bang theory also implies that the universe has no center. Instead, the expansion occurs uniformly everywhere, meaning every point in the universe is moving away from every other point. This uniform expansion challenges our intuitive notions of size and scale. The universe doesn't expand into pre-existing space. Space itself expands, carrying galaxies with it. The accelerating expansion due to dark energy suggests that distant regions of the universe will eventually move beyond our observational reach. This implies that the observable universe will shrink in terms of the regions we can study. The Big Bang theory also affects our understanding of the universe's shape. Current evidence suggests a flat universe on large scales, which, combined with inflation, supports the idea of an infinite or extremely large universe. Overall, the Big Bang theory provides a framework for understanding the dynamic and ever-expanding nature of the universe. It shapes our perception of the cosmos's size, from the observable limits to the potential infinity beyond. Future predictions based on the Big Bang theory continue to evolve as our understanding of the universe deepens. One key prediction is the ongoing expansion of the universe, driven by dark energy. As dark energy accelerates the expansion, distant galaxies will move farther away, eventually becoming invisible to us. This means the observable universe will contain fewer galaxies over time. The universe's expansion will lead to a colder and darker cosmos. As galaxies drift apart, star formation will slow, and existing stars will burn out, leaving behind remnants like white dwarfs, neutron stars, and black holes. Eventually, the universe may enter a phase known as the heat death, or big freeze. In this scenario, the universe reaches a state of maximum entropy, where no usable energy remains, and all processes cease. The Big Bang theory also predicts the fate of cosmic structures. Galaxy clusters and superclusters will remain bound by gravity, but isolated galaxies will drift into the void, separating from each other indefinitely. On a smaller scale, predictions include the continued formation and evolution of stars and planetary systems. Stellar evolution models, grounded in Big Bang principles, help us forecast the life cycles of different types of stars. The theory suggests that black holes will play a significant role in the universe's distant future. Over trillions of years, black holes will dominate as other forms of matter and energy dissipate. Hawking radiation predicts that black holes will eventually evaporate, albeit over timescales far beyond the current age of the universe. This process will leave behind a universe with very few particles and low energy. Cosmic inflation, a cornerstone of the Big Bang theory, implies the possibility of a multiverse. If inflation occurred, it could have produced many other bubble universes, each with different properties and laws of physics. Another prediction is the potential for discovering new particles and forces. The early universe's extreme conditions may have created particles we have yet to detect, expanding our understanding of fundamental physics. As observational techniques improve, we may refine measurements of the Hubble constant and other cosmological parameters. This will enhance predictions about the universe's expansion rate and ultimate fate. The Big Bang theory also predicts the presence of primordial gravitational waves. Detecting these waves would provide insights into the universe's earliest moments, including the inflationary period. Dark matter remains a significant mystery. The Big Bang framework predicts its influence on galaxy formation and structure. Future discoveries could reveal its nature and role in the universe. Ongoing research into dark energy aims to understand its properties and origins. This mysterious force shapes the universe's expansion, and unlocking its secrets could revolutionize cosmology. Ultimately, predictions based on the Big Bang theory emphasize a dynamic, ever-changing universe. As we continue to explore and understand the cosmos, our theories and predictions will evolve, guided by new discoveries and insights. The question of whether the universe is infinite is both profound and complex. Understanding this concept involves defining what we mean by the universe and the implications of its possible infinity. The universe encompasses all of space, time, matter, and energy. It includes everything from the smallest particles to the largest structures, as well as the physical laws that govern them. When we ask if the universe is infinite, we're considering whether it has an end or boundary. An infinite universe would have no limits in space or time, extending endlessly in all directions. The importance of this question lies in its fundamental nature. Knowing whether the universe is finite or infinite influences our understanding of cosmology, physics, and the nature of reality itself. If the universe is infinite, it might contain infinite possibilities. This has implications for the multiverse theory, suggesting that there could be countless other universes with different physical laws and constants. An infinite universe also affects our understanding of time and space. It challenges our concepts of beginning and end, suggesting that the universe may have no starting point or final state. The concept of infinity has philosophical implications as well. It forces us to reconsider our place in the cosmos and the nature of existence, posing deep questions about the meaning of life and the universe. Scientifically, determining the universe's size and shape helps refine our models of cosmology. It guides our understanding of the Big Bang, cosmic inflation, and the ultimate fate of the universe. An infinite universe would mean that every possible event, however unlikely, could occur somewhere. This idea leads to intriguing questions about the nature of probability and the uniqueness of our own existence. The quest to determine if the universe is infinite drives technological advancements. It requires precise instruments and innovative methods to observe the cosmos and measure its properties. Understanding the universe's size also impacts our search for extraterrestrial life. An infinite universe increases the likelihood that life exists elsewhere, potentially in forms vastly different from our own. The concept of an infinite universe intersects with ideas of dark matter and dark energy. These mysterious components make up most of the universe's mass energy content and influence its expansion and structure. Exploring the infinity of the universe involves both observation and theory. It requires a combination of empirical data from telescopes and satellites and theoretical models based on the laws of physics. The importance of this question extends to our everyday understanding of the world. It shapes how we view our planet, our place in the cosmos, and the potential for discovering new phenomena. Ultimately, the question of whether the universe is infinite touches on the core of human curiosity. It represents our desire to understand the vast, complex reality we inhabit, driving our exploration and discovery. The role of dark energy in the universe's expansion is a critical aspect of modern cosmology. Dark energy is a mysterious force that makes up about 68% of the universe's total energy density. Observations show that the universe's expansion is accelerating, which is attributed to the influence of dark energy. This acceleration was a surprising discovery, changing our understanding of cosmic dynamics. Dark energy works against the force of gravity, causing galaxies to move away from each other at an increasing rate. This expansion suggests that the universe will continue to grow indefinitely. The exact nature of dark energy remains one of the biggest questions in physics. It's thought to be a property of space itself, exerting a repulsive force that drives the accelerated expansion. And dark energy's influence is not constant throughout the universe's history. Early in the universe, matter dominated, slowing the expansion. As the universe expanded, dark energy became more influential, accelerating the expansion. Cosmologists use the cosmological constant, introduced by Einstein, to describe dark energy. The cosmological constant represents a uniform energy density filling space, consistent with dark energy's properties. Alternative theories suggest that dark energy might vary over time or interact with matter and radiation. These theories are still under investigation, with observations aimed at distinguishing between them. Understanding dark energy is crucial for predicting the universe's ultimate fate. If the acceleration continues, the universe could end in a big freeze, where galaxies move beyond each other's reach, leading to a cold, dark, and empty cosmos. Dark energy affects the large-scale structure of the universe. It influences the formation and distribution of galaxies and clusters, impacting the overall architecture of the cosmos. Gravitational lensing, where light is bent by massive objects, helps map dark energy's effects. By studying lensing patterns, scientists can infer the distribution and properties of dark energy. The study of type Ia supernovae, which serve as standard candles, has provided key evidence for dark energy. These supernovae reveal how the expansion rate has changed over time, highlighting dark energy's role. Dark energy's impact extends to the cosmic microwave background. It affects the CMB's temperature fluctuations and polarization patterns, offering insights into the universe's expansion history. Current and future missions aim to measure dark energy's properties more precisely. Telescopes like the Euclid and the James Webb Space Telescope will provide new data to refine our understanding. The role of dark energy in the universe's expansion is a profound topic, linking fundamental physics with cosmological observations. It shapes our understanding of the universe's past, present, and future. As research continues, dark energy remains a central focus of cosmology, driving the quest to unravel the mysteries of the expanding universe and the forces that govern it. Evidence for the expanding universe first came from Edwin Hubble's observations. He discovered that galaxies are moving away from us, with their speed proportional to their distance. This relationship is known as Hubble's law. The redshift of light from distant galaxies supports the expansion theory. As galaxies move away, their light stretches to longer, redder wavelengths, providing a measurable indicator of their motion. The cosmic microwave background radiation is another key piece of evidence. This faint glow, a remnant from the early universe, shows the universe was once hot and dense and has been expanding and cooling over time. Measurements of the cosmic microwave background by missions like COBE, WMAP, and Planck have provided detailed maps of temperature fluctuations. These fluctuations are imprints of the early universe's density variations. Type Ia supernovae have been crucial in understanding the universe's accelerated expansion. These exploding stars serve as standard candles, allowing astronomers to measure distances accurately and reveal changes in the expansion rate. The discovery of dark energy was a major milestone. Observations of distant supernovae showed that the universe's expansion is accelerating, implying the existence of a mysterious force driving this acceleration. Galaxy surveys, such as the Sloan Digital Sky Survey, map the large-scale structure of the universe. These surveys reveal how galaxies are distributed and provide insights into the universe's expansion history. Gravitational lensing offers additional evidence. Light from distant objects is bent by massive galaxies and clusters, allowing scientists to study the distribution of dark matter and dark energy. Baryon acoustic oscillations are subtle imprints in the distribution of galaxies, reflecting sound waves from the early universe. These oscillations serve as a cosmic ruler, helping to measure the expansion rate. Observations of the Hubble constant, which describes the expansion rate, have been refined over time. Different methods, including cosmic microwave background data and local measurements, provide converging evidence for expansion. The study of galaxy clusters provides clues about the universe's expansion. The distribution and movement of clusters, influenced by dark matter and dark energy, help refine cosmological models. X-ray observations of galaxy clusters reveal information about the hot gas within them. This data contributes to our understanding of the universe's matter content and its expansion dynamics. Cosmic voids, large empty spaces between galaxy clusters, also play a role. Studying these voids helps scientists understand the large-scale structure and the influence of dark energy on expansion. The cosmic infrared background, a faint glow from the accumulation of light from distant galaxies, provides further evidence of the universe's history and expansion. These discoveries and observations collectively support the theory of an expanding universe. Each piece of evidence contributes to a comprehensive understanding of the cosmos, its origins, and its ultimate fate. Dark matter and dark energy are two of the most intriguing mysteries in modern cosmology. They make up about 95% of the universe's total mass energy content, yet we cannot see or directly detect them. Dark matter is thought to be a form of matter that does not interact with electromagnetic forces, making it invisible to current instruments. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. One leading theory suggests that dark matter consists of weakly interacting massive particles, or WIMPs. These particles would be abundant in the universe and interact primarily through gravity and possibly the weak nuclear force. Another theory proposes axions as dark matter candidates. Axions are hypothetical particles that could solve certain problems in quantum chromodynamics and provide the needed dark matter mass. Some scientists explore the idea of sterile neutrinos, which do not interact through the standard weak force, but could contribute to dark matter. These particles would be heavier than regular neutrinos and harder to detect. Modified Newtonian dynamics, or MOND, is an alternative theory that modifies the laws of gravity to explain the effects attributed to dark matter. It suggests that at very low accelerations, gravity behaves differently than predicted by Newton and Einstein. Dark energy, on the other hand, is a form of energy that permeates all of space and accelerates the universe's expansion. It is even more mysterious than dark matter and is often described through the cosmological constant, lambda, in Einstein's equations. Some theories propose that dark energy is a property of space itself, a vacuum energy that remains constant over time. This concept aligns with the cosmological constant, where dark energy density does not change as the universe expands. Another theory suggests that dark energy could be dynamic, evolving over time. This idea is known as quintessence, where a new scalar field could be responsible for the accelerating expansion, varying its influence as the universe ages. Phantom energy is a speculative form of dark energy that could cause the expansion to accelerate to such an extent that it eventually tears apart galaxies, stars, planets, and even atomic nuclei in a hypothetical scenario known as the Big Rip. The interaction between dark matter and dark energy is also a subject of study. Some theories explore whether these two components influence each other, or if their effects are entirely separate. Understanding the nature of dark matter and dark energy is crucial for a complete theory of cosmology. They affect the formation and evolution of cosmic structures, influencing the universe's fate. Experiments and observations, such as those conducted by the Large Hadron Collider, aim to detect dark matter particles directly or through their decay products. These efforts could provide crucial evidence for the nature of dark matter. Observations of the cosmic microwave background, galaxy distributions, and supernovae help refine models of dark energy. These data constrain its properties and improve our understanding of its role in the universe's expansion. The search for dark matter and dark energy continues to drive advancements in technology and theoretical physics. Discovering their true nature would be a monumental step in understanding the cosmos and our place within it. Despite significant advancements, the universe remains filled with unsolved mysteries. Dark matter and dark energy, while central to our understanding, are still not fully understood. One major mystery is the true nature of dark matter. We know it exists because of its gravitational effects, but we have yet to identify the particles that compose it. Similarly, the origin and properties of dark energy remain elusive. We observe its influence on the universe's expansion, but its underlying mechanism is still a profound mystery. The question of what happened before the Big Bang also puzzles scientists. Current theories describe the universe's evolution from a hot, dense state, but the events preceding the Big Bang are still speculative. The exact cause of cosmic inflation, the rapid expansion of the universe just after the Big Bang, is another unsolved mystery. While inflation theory is well supported, the trigger for this event is not fully understood. The fate of the universe is still uncertain. Depending on the properties of dark energy and the overall geometry of the universe, it could expand forever, collapse in a big crunch, or experience a big rip. The nature of black holes and what happens inside them is another area of ongoing research. The singularity at a black hole's center, where gravity becomes infinite, defies our current understanding of physics. Gravitational waves, while now observed, still hold many secrets. Detecting more of these waves and understanding their sources can reveal new information about extreme cosmic events. The unification of general relativity and quantum mechanics is a major goal in physics. A theory of quantum gravity would reconcile these two fundamental frameworks, but such a theory remains elusive. Neutrinos, ghostly particles that pass through matter almost undisturbed, are still not fully understood. Their exact masses and the role they play in the universe's evolution are key questions. The nature of time itself is a profound mystery. Understanding why time flows in one direction and how it relates to the overall structure of the universe is an ongoing challenge. The potential existence of parallel universes, or a multiverse, is another intriguing but unresolved topic. Evidence for or against other universes would have profound implications for our understanding of reality. The composition and behavior of the universe's first moments remain a significant area of research. Understanding how the first stars and galaxies formed can provide insights into the universe's early conditions. The mysterious cold spot in the cosmic microwave background could suggest new physics or unusual cosmic events. Determining its origin is an active area of investigation. These unsolved mysteries highlight the vastness and complexity of the universe. Each discovery leads to new questions, driving the relentless pursuit of knowledge in cosmology and beyond. The shape of the universe is a fundamental question in cosmology, with three main possibilities: flat, open, and closed. Each shape has different implications for the universe's geometry and fate. A flat universe follows the rules of Euclidean geometry. Parallel lines remain parallel, and the angles of a triangle add up to 180 degrees. Observations suggest that our universe is very close to flat. In a flat universe, the expansion could continue indefinitely, slowing down over time but never completely stopping. This shape aligns with current measurements of the cosmic microwave background and galaxy distributions. An open universe has a hyperbolic geometry. Here, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. This shape implies a universe that expands forever at an increasing rate. In an open universe, the overall density of matter and energy is less than the critical density needed to halt the expansion. This results in a saddle-shaped geometry, expanding infinitely, but never collapsing. A closed universe has a spherical geometry. Parallel lines eventually converge, and the angles of a triangle add up to more than 180 degrees. This shape suggests a finite universe that curves back on itself. In a closed universe, the density of matter and energy is greater than the critical density. This could eventually lead to the expansion halting and the universe collapsing back in a big crunch. Determining the universe's shape involves measuring the cosmic microwave background. Tiny fluctuations in this radiation provide clues about the curvature of space. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided high-precision measurements, indicating that the universe is nearly flat. However, slight deviations could suggest a more complex shape. The shape of the universe also affects its fate. A flat or open universe would expand forever, possibly leading to a big freeze where stars burn out and galaxies drift apart in an increasingly cold and empty space. A closed universe, on the other hand, might end in a big crunch. After expanding for billions of years, it could collapse back into a hot, dense state, possibly leading to another Big Bang. The concept of inflation helps explain why the universe appears flat. Inflation theory proposes a rapid expansion shortly after the Big Bang, smoothing out any initial curvature and driving the universe towards flatness. Observations of large-scale structures, such as galaxy clusters and voids, also provide information about the universe's shape. These structures form patterns that can hint at the underlying geometry. Gravitational lensing, the bending of light by massive objects, offers another method to study the universe's shape. By analyzing how light is distorted, scientists can infer the curvature of space. While current evidence supports a nearly flat universe, ongoing research aims to refine these measurements. Understanding the universe's shape is crucial for a complete picture of its origin, structure, and ultimate fate. Current evidence on the shape of the universe comes from several key observations and measurements. The most significant data comes from the cosmic microwave background radiation. The Wilkinson Microwave Anisotropy Probe, or WMAP, provided detailed maps of the CMB. These maps showed that the universe is very close to flat, with only slight deviations possible. The Planck satellite, which followed WMAP, offered even higher precision measurements. Planck's data reinforced the conclusion that the universe is nearly flat, with any curvature being extremely small. Observations of large-scale structures, such as galaxy clusters, also support a flat universe. The distribution and behavior of these structures align with predictions made by models assuming a flat geometry. Type Ia supernovae have been used as standard candles to measure cosmic distances. Their observations indicate an accelerating expansion, consistent with a flat universe driven by dark energy. Baryon acoustic oscillations provide another line of evidence. These regular periodic fluctuations in the density of visible matter fit well with a flat universe model. Gravitational lensing, where light from distant objects is bent by massive structures, helps map the curvature of space. Studies of lensing patterns support the idea of a flat or nearly flat universe. The cosmic microwave background's temperature fluctuations offer clues about the universe's shape. These fluctuations match the patterns expected in a flat universe. The combination of CMB data, supernova observations, and large-scale structure surveys create a consistent picture. All these lines of evidence point toward a universe that is very close to flat. Current measurements suggest that if the universe is curved, the curvature is so slight that it is indistinguishable from flatness on the scales we can observe. The concept of inflation helps explain these findings. Inflation theory predicts that the rapid expansion of the early universe would drive it towards flatness, smoothing out any initial curvature. Dark energy's influence on the universe's expansion also fits within a flat universe model. The observed acceleration of the expansion is consistent with the effects of dark energy in a flat universe. While the evidence strongly favors a flat universe, slight deviations could exist. Future observations with even greater precision might reveal subtle curvature that we have yet to detect. Ongoing missions and advanced telescopes will continue to refine our measurements. These efforts aim to further narrow down the universe's shape, providing more definitive answers. Understanding the universe's shape is fundamental to cosmology. It informs our models of the universe's origin, evolution, and ultimate fate, shaping our comprehension of the cosmos. The shape of the universe has profound implications for its overall structure and future. If the universe is flat, it means it will likely expand forever, but at an accelerating rate due to dark energy. A flat universe suggests that the total density of matter and energy is precisely balanced with the critical density. This balance allows the universe to continue expanding indefinitely without collapsing back on itself. In a flat universe, the geometry follows Euclidean principles, meaning that parallel lines remain parallel and the angles of a triangle add up to 180 degrees. This has implications for how we understand space and distance on cosmic scales. If the universe is open, it implies a hyperbolic geometry. This means that the universe has a negative curvature, causing parallel lines to diverge and the angles of a triangle to add up to less than 180 degrees. An open universe would expand forever at an increasing rate, but the expansion would slow over time. This scenario suggests that the universe's overall density is less than the critical density required to halt the expansion. The geometry of an open universe affects how we observe and measure distant objects. Distances between galaxies would appear larger than in a flat universe, influencing our perception of the universe's scale. A closed universe, on the other hand, has a spherical geometry. This means that the universe has a positive curvature, causing parallel lines to eventually converge and the angles of a triangle to add up to more than 180 degrees. In a closed universe, the total density of matter and energy exceeds the critical density. This would eventually cause the expansion to halt and reverse, leading to a big crunch where the universe collapses back into a hot, dense state. The geometry of a closed universe means that it is finite in size but unbounded. If you traveled far enough in one direction, you would eventually return to your starting point, similar to traveling on the surface of a sphere. The fate of a closed universe is significantly different from that of a flat or open universe. The eventual collapse in a big crunch could potentially lead to a new Big Bang, suggesting a cyclic model of the universe. The implications of each shape also extend to the formation and evolution of cosmic structures. The density and geometry influence how galaxies, clusters, and superclusters form and evolve over time. In a flat or open universe, galaxies continue to move apart, and new stars may form for a while, but eventually star formation will cease, leading to a big freeze. In a closed universe, galaxies might eventually merge as the universe contracts. Understanding the shape of the universe helps refine our cosmological models and theories. It influences how we interpret observations and how we think about the universe's past, present, and future. The shape of the universe also has philosophical and existential implications. It affects how we perceive our place in the cosmos and the ultimate fate of everything within it. Continued observations and advancements in technology will help us determine the universe's shape with greater precision, shedding light on these profound questions and guiding our understanding of the cosmos. The shape of the universe directly influences the concept of infinity. In a flat universe, the geometry allows for the possibility of an infinite expanse. Space extends indefinitely in all directions without ever looping back on itself. If the universe is flat and infinite, it suggests that there are endless regions of space beyond our observable horizon. This would mean the universe contains an infinite number of galaxies, stars, and possibly even other forms of life. An open universe also supports the idea of infinity. With its hyperbolic geometry, space continues to expand forever, becoming more vast and more dispersed as time goes on. In this scenario, space is not only infinite but also eternally expanding. In an open universe, the infinite expanse means that new regions of space are continually created. This could result in an ever-growing universe where matter and energy become increasingly diluted. A closed universe, however, complicates the concept of infinity. With its spherical geometry, a closed universe is finite, but unbounded. This means that while the universe has a limited volume, you could travel endlessly without ever encountering an edge. In a closed universe, infinity is expressed through the endless loop of space. Traveling far enough in one direction would eventually bring you back to your starting point, much like circumnavigating the globe. The finite nature of a closed universe implies a different kind of infinity. Instead of an infinite expanse, it offers an infinite journey within a bounded space, where paths can loop endlessly. The shape of the universe also affects our understanding of time and infinity. In a flat or open universe, time might stretch infinitely into the future, suggesting that the universe could exist forever. In a closed universe, the cyclical nature could imply a finite timeline, where the universe undergoes endless cycles of expansion and contraction, each cycle potentially resetting the cosmic clock. The concept of cosmic horizons is also influenced by the universe's shape. In a flat or open universe, the observable horizon continually recedes as the universe expands, but there is always more beyond it. In a closed universe, the observable horizon might be limited by the curvature of space. Beyond this horizon, space curves back on itself, creating a finite observable region within an unbounded loop. The implications for infinity also extend to the multiverse theory. If our universe is flat or open and infinite, it might be one of many such universes, each potentially infinite in its own right. In a closed universe, the multiverse concept could still hold, but each individual universe might be finite yet unbounded, existing within a larger, possibly infinite multiverse framework. Understanding how the shape of the universe affects infinity helps refine our cosmological models and theories. It guides our interpretations of observations and deepens our insights into the nature of the cosmos. The relationship between shape and infinity is a profound aspect of cosmology, challenging our perceptions and expanding our understanding of the universe's true nature. SpaceTime is a fundamental concept in understanding the universe. It combines the three dimensions of space with the dimension of time into a single four-dimensional continuum. Albert Einstein's theory of general relativity revolutionized our understanding of spacetime. According to this theory, massive objects cause spacetime to curve, and this curvature is what we perceive as gravity. The warping of spacetime by mass affects the motion of objects. For example, planets orbit the Sun because they are following the curved paths in spacetime created by the Sun's mass. Spacetime is not static. It is dynamic and can be influenced by the distribution of matter and energy in the universe. This means that as the universe expands, spacetime itself is stretching. The concept of spacetime is crucial for understanding the Big Bang. The Big Bang was not an explosion in space, but rather an expansion of spacetime itself, starting from a highly dense and hot state. Gravitational waves, ripples in spacetime caused by violent cosmic events, provide direct evidence of the dynamic nature of spacetime. These waves were predicted by Einstein and first detected by LIGO in 2015. Spacetime plays a critical role in the formation of cosmic structures. The initial tiny fluctuations in spacetime's fabric, as seen in the cosmic microwave background, grew over billions of years into galaxies and clusters. Black holes are regions where spacetime is curved to such an extreme that not even light can escape. The event horizon of a black hole marks the boundary beyond which spacetime is so warped that escape is impossible. The study of spacetime is also essential for understanding dark matter and dark energy. Dark matter influences the curvature of spacetime on large scales, while dark energy affects the overall expansion of spacetime. In the context of the universe's shape, spacetime can have different geometries, flat, open, or closed. These geometries influence how spacetime curves and expands. A flat, space-time geometry suggests that the universe will expand forever at a steady rate, whereas an open geometry indicates an accelerating expansion. A closed geometry could eventually lead to a contraction. The interplay between space-time and the universe's expansion is a central theme in cosmology. Understanding how space-time evolves helps scientists predict the future behavior of the universe. Space-time also affects the passage of time. According to general relativity, time can slow down in stronger gravitational fields, an effect observed near massive objects like stars and black holes. The study of space-time extends to quantum gravity, which seeks to reconcile general relativity with quantum mechanics. This area of research aims to understand space-time at the smallest scales, where quantum effects dominate. Overall, space-time is the stage on which the drama of the universe unfolds. It is fundamental to understanding gravity, the expansion of the universe, and the behavior of matter and energy across the cosmos. Hubble's law is a fundamental discovery in cosmology, describing the relationship between a galaxy's distance and its velocity as it moves away from us. This law is named after Edwin Hubble, who first observed this phenomenon in the 1920s. Hubble's observations showed that galaxies are receding from us, with their speed proportional to their distance. This means that the farther away a galaxy is, the faster it appears to be moving away. The velocity of a galaxy can be measured through its redshift. Redshift occurs when the light from a galaxy is stretched to longer, redder wavelengths as it travels through expanding space. Redshift is a key indicator of the universe's expansion. As space itself expands, it stretches the light traveling through it, causing this shift towards the red end of the spectrum. Hubble's law can be expressed mathematically as v t 0 d, where v is the velocity of the galaxy, h0 is the Hubble constant, and d is the distance to the galaxy. This relationship provides a way to measure the rate of the universe's expansion. The Hubble constant is crucial for determining the age and size of the universe. By measuring the rate of expansion, scientists can estimate how long the universe has been expanding since the Big Bang. The discovery of redshift was initially made by Melvin Slipher, who observed the spectral lines of galaxies shifting towards the red end. Hubble built on these observations to establish the broader relationship now known as Hubble's law. Hubble's law provided strong evidence for the Big Bang theory. It showed that the universe is not static, but dynamic, continually expanding from an initial explosive event. The redshift of distant galaxies also supports the idea of an expanding universe. As we observe galaxies farther away, we see light that has traveled for billions of years, stretched by the expansion of space over that time. The concept of redshift is not limited to visible light. It applies to all forms of electromagnetic radiation, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. Hubble's law has been refined over the years with more precise measurements. Modern instruments like the Hubble Space Telescope have provided more accurate values for the Hubble constant. Understanding redshift also helps astronomers study the large-scale structure of the universe. By measuring redshifts of many galaxies, they can map the distribution of galaxies and cosmic structures. The relationship between redshift and distance is also used to study the effects of dark energy. Observations of distant supernovae show that the expansion rate is accelerating, influenced by this mysterious force. Hubble's law and redshift have transformed our understanding of the cosmos. They provide a framework for studying the universe's history, its current state, and its future evolution. These concepts continue to be central to cosmology, guiding our exploration of the universe and helping us uncover its deepest mysteries. The discovery of the universe's expansion is one of the most significant milestones in modern astronomy. It fundamentally changed our understanding of the cosmos. In the early 20th century, most scientists believed the universe was static and unchanging. This view was challenged by new observations and theoretical developments. Edwin Hubble played a pivotal role in discovering the universe's expansion. Using the Hooker telescope at Mount Wilson Observatory, he observed distant galaxies and measured their redshifts. Hubble's work built on the earlier efforts of Melvin Slipher, who had discovered that many galaxies exhibited redshifts, indicating they were moving away from us. Hubble and his colleague Milton Humersel systematically measured the distances to these galaxies using Cepheid variable stars as standard candles. They found a correlation between the distance of galaxies and their redshift. This correlation led to the formulation of Hubble's law, which states that the recessional velocity of a galaxy is directly proportional to its distance from us. This relationship provided clear evidence that the universe is expanding. The discovery was groundbreaking because it supported the Big Bang theory, suggesting that the universe had a beginning and has been expanding ever since. Hubble's observations showed that the universe is not static but dynamic. This realization had profound implications for cosmology, indicating that the universe's history and future are shaped by its expansion. The expanding universe model resolved several paradoxes of the static universe theory, such as Olber's paradox, which questioned why the night sky is dark if the universe is infinite and eternal. The discovery of the expanding universe also prompted new theoretical work, including the development of models that describe the universe's evolution over time. Einstein's theory of general relativity played a crucial role in understanding the implications of an expanding universe. Initially, Einstein had introduced a cosmological constant to maintain a static universe model, but he later called this his greatest blunder after Hubble's discovery. Subsequent observations have confirmed and refined Hubble's initial findings. Improved technology and techniques have provided more accurate measurements of the expansion rate. The discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson provided further evidence for the Big Bang and the expanding universe, showing that the universe began in a hot, dense state. Today, the study of the universe's expansion includes exploring the effects of dark energy, which accelerates the expansion. This has led to the concept of an ever-expanding universe that will continue to grow indefinitely. The discovery of the universe's expansion remains a cornerstone of cosmology. It continues to inspire research and exploration, driving our quest to understand the origins, structure, and ultimate fate of the cosmos. The rate of expansion of the universe is quantified by the Hubble constant. This value represents the rate at which galaxies are receding from us due to the expansion of space. Determining the Hubble constant has been a major goal in cosmology. Accurate measurements are crucial for understanding the age, size, and future evolution of the universe. Initially, Edwin Hubble estimated the Hubble constant to be around 500 kilometers per second per megaparsec. This value has been refined over the years with better data and methods. Modern measurements have provided more precise values for the Hubble constant, though there is still some disagreement. Current estimates range from about 67 to 74 kilometers per second per megaparsec. Two primary methods are used to measure the Hubble constant. One involves observing the cosmic microwave background, while the other relies on the distance and redshift of galaxies and supernovae. The cosmic microwave background method uses data from satellites like WMAP and Planck. These observations offer a snapshot of the early universe, allowing scientists to infer the expansion rate. The galaxy and supernova method involves measuring distances to galaxies using standard candles, such as Cepheid variables and type Ia supernovae. By comparing these distances to the redshifts, the expansion rate can be calculated. Discrepancies between these methods have sparked significant debate. The difference in value suggests there may be new physics beyond our current understanding, or it might be due to systematic errors in measurements. The expansion rate is not constant over time. Early in the universe's history, the expansion was decelerated by gravity. However, about 5 billion years ago, the influence of dark energy began to accelerate the expansion. Understanding the rate of expansion is key to determining the universe's ultimate fate. If the expansion continues to accelerate, the universe could end in a big freeze, where galaxies drift apart and stars burn out. Precise measurements of the Hubble constant also help refine our models of cosmic inflation, the rapid expansion that occurred just after the Big Bang. These models shape our understanding of the universe's earliest moments. The rate of expansion affects the formation and distribution of large-scale structures in the universe. Galaxy clusters, superclusters, and voids are all influenced by the expansion dynamics. The Hubble constant is also linked to the universe's critical density, the dividing line between different geometries. Accurate measurements help determine whether the universe is flat, open, or closed. Future missions and advanced technologies aim to resolve the discrepancies in the Hubble constant. Projects like the James Webb Space Telescope and the Euclid mission will provide more data to refine our understanding. The rate of expansion is a fundamental aspect of cosmology. It connects the universe's past, present, and future, guiding our exploration of the cosmos and the laws that govern it. Theories on the future expansion of the universe revolve around the influence of dark energy and the overall curvature of space. One theory is the Big Freeze, where the universe continues to expand forever, cooling and growing more sparse. In the Big Freeze scenario, galaxies move away from each other, and new star formation eventually ceases. Existing stars burn out, leaving behind white dwarfs, neutron stars, and black holes. Another theory is the Big Rip. If dark energy increases in strength over time, it could eventually tear apart galaxies, stars, and even atomic nuclei. This would end the universe in a violent, disintegrative event. The Big Crunch is an alternative theory where the expansion of the universe slows and reverses. Eventually, the universe would collapse back into a hot, dense state, potentially leading to a new Big Bang. The possibility of a cyclic universe arises from the Big Crunch scenario. After collapsing, the universe might bounce back in another Big Bang, starting a new cycle of expansion and contraction. The role of dark energy is crucial in these theories. If dark energy remains constant, the universe will likely continue expanding indefinitely. If it changes over time, the fate of the universe could be very different. Quintessence is a theory where dark energy is dynamic, evolving over time. Depending on its properties, quintessence could lead to a variety of future scenarios, including continued expansion or eventual collapse. Phantom energy, a more extreme form of dark energy, predicts the Big Rip. In this scenario, dark energy's repulsive force grows stronger, overcoming all other forces and leading to the universe's destruction. The study of cosmic inflation, which describes the rapid expansion of the early universe, also provides insights into future expansion. Inflationary models can predict long-term behavior based on initial conditions. Observations of the cosmic microwave background help refine these models. By studying the CMB, scientists can infer the universe's expansion history and make more accurate predictions about its future. Theories on future expansion also consider the role of dark matter. While dark energy drives expansion, dark matter influences the formation and stability of cosmic structures. Their interplay is critical for understanding long-term outcomes. The flatness problem, addressed by inflation theory, suggests that the universe's geometry is very close to flat. This supports the idea of endless expansion, but does not rule out other possibilities. Advanced telescopes and missions aim to measure dark energy's properties more precisely. Understanding its nature will help determine which future expansion theory is most likely. The ultimate fate of the universe is a profound question in cosmology. Each theory offers different implications for the long-term evolution of space, time, and matter. Continued research and observation are essential. As our understanding of dark energy and cosmic expansion improves, we will gain deeper insights into the universe's destiny and our place within it. The future expansion of the universe has profound implications for the concept of infinity. If the universe expands forever, it suggests an infinite future, where time continues without end. An ever-expanding universe implies that space itself is infinite. As galaxies move apart, new regions of space are created, extending the boundaries of the cosmos indefinitely. The idea of an infinite universe raises questions about the nature of reality. In an infinite space, every possible event, no matter how improbable, could occur somewhere. The concept of infinity also influences our understanding of the multiverse. If our universe is infinite, it might be one of countless other universes, each with its own laws of physics and constants. Infinity challenges our comprehension of space and time. It suggests that the universe has no boundaries, and time may never cease, offering a limitless arena for cosmic evolution. Theories like the Big Rip complicate the notion of infinity. If the universe ends in a cataclysmic event, it suggests that infinity has limits, constrained by the forces that govern cosmic expansion. A cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction, offers a different view of infinity. Here, infinity is not a linear progression but a series of recurring events. The Big Crunch and subsequent rebirth in a new Big Bang present a model of infinite cycles. Each cycle represents a finite period, but the process itself is infinite, continuously renewing the universe. Philosophically, the concept of infinity in cosmology intersects with ideas of eternal recurrence and the nature of time. It challenges us to rethink the linear progression of time and consider the possibility of endless repetition. Infinity in an expanding universe also impacts the search for extraterrestrial life. In an infinite universe, the probability of life existing elsewhere increases, suggesting that intelligent civilizations could be numerous. The infinite expansion of space affects the fate of cosmic structures. Galaxies, stars, and planets will drift apart, becoming isolated in an ever-growing void, leading to an infinite dilution of matter. Dark energy's role in driving infinite expansion adds another layer of complexity. Understanding dark energy's properties is crucial for determining whether the universe's expansion will indeed continue indefinitely. The concept of an infinite universe influences theoretical physics and cosmology, pushing scientists to explore beyond the observable universe and consider realms that are currently beyond our reach. Infinity also has implications for entropy and the second law of thermodynamics. In an infinite universe, the gradual increase of entropy leads to a state of maximum disorder, impacting the ultimate fate of cosmic evolution. The interplay between cosmic expansion and infinity remains a central theme in cosmology. It challenges our understanding of the universe's nature, driving ongoing research and philosophical inquiry into the infinite possibilities of the cosmos. The multiverse is a hypothetical collection of multiple universes, including our own. Each universe within the multiverse is called a parallel universe or alternate universe. The idea of the multiverse arises from various theories in physics and cosmology. It suggests that there could be countless other universes, each with its own set of physical laws and constants. One of the key concepts supporting the multiverse theory is cosmic inflation. According to this theory, different regions of space could stop inflating at different times, creating separate bubble universes. In these bubbly universes, the properties of matter, energy, and fundamental forces could vary, leading to diverse and unique cosmic environments. This could mean that some universes are vastly different from our own. Quantum mechanics also suggests the possibility of a multiverse. The many-worlds interpretation proposes that every quantum event spawns multiple, branching realities, each representing a different outcome. String theory, another leading framework in theoretical physics, supports the multiverse concept. It posits the existence of extra dimensions beyond our familiar three-dimensional space, which could host other universes. The multiverse idea expands the scope of cosmology. Instead of focusing solely on our own universe, it encourages scientists to consider the broader ensemble of possible universes. One implication of the multiverse is the anthropic principle, which explains why the physical constants in our universe appear fine-tuned for life. In an infinite multiverse, all possible values for these constants exist somewhere. The multiverse could also provide answers to some of the biggest questions in physics, such as the nature of dark matter and dark energy. Different universes might contain different amounts or forms of these mysterious substances. While the multiverse is a compelling concept, it remains speculative. Direct evidence is challenging to obtain, and much of the support comes from theoretical predictions and indirect observations. Critics argue that the multiverse is untestable and therefore not a scientific hypothesis. However, proponents believe that as our understanding of physics advances, we might find ways to test multiverse theories. The multiverse raises philosophical questions about the nature of reality and our place within it. If other universes exist, it challenges our understanding of existence and uniqueness. Some scientists suggest that black holes could be gateways to other universes. This idea is based on the concept that black holes might connect different regions of space-time, potentially linking separate universes. The study of the multiverse also intersects with mathematics and computer science. Concepts like infinity, probability, and information theory play crucial roles in developing and understanding multiverse models. Ultimately, the multiverse is one of the most intriguing and far-reaching ideas in modern science. It pushes the boundaries of our imagination and opens up a vast realm of possibilities for exploring the fundamental nature of reality. There are several different types of multiverses proposed by scientists and theorists, Each type suggests a unique way in which multiple universes could exist. The first type is the bubble multiverse, based on the theory of eternal inflation. This idea suggests that our universe is one of many bubbles that stopped inflating while others continue to inflate, creating separate, isolated universes. Another type is the membrane, or brain multiverse, which comes from string theory. It proposes that our universe is a three-dimensional brain embedded in a higher dimensional space, with other brains representing parallel universes. The quantum multiverse arises from the many worlds interpretation of quantum mechanics. According to this view, every quantum event spawns multiple branching realities, each representing different outcomes. The cyclic multiverse, or oscillating universe theory, suggests that the universe goes through endless cycles of big bangs and big crunches. Each cycle creates a new universe with potentially different properties. The landscape multiverse is derived from string theory's idea of a vast landscape of possible vacua. Each vacuum state corresponds to a different universe with its own physical laws and constants. The holographic multiverse theory suggests that our three-dimensional universe might be a holographic projection of information encoded on a distant, lower dimensional boundary. The simulated multiverse proposes that our universe could be one of many simulations created by an advanced civilization. This idea explores the possibility that reality as we know it might be an artificial construct. The mathematical multiverse posits that all mathematically consistent structures exist as physical realities. Every possible mathematical structure corresponds to a different universe with its own laws and properties. The black hole multiverse theory speculates that black holes might create new universes on the other side of their event horizons. Each black hole could potentially lead to a different universe with unique characteristics. In the parallel universes of the many worlds interpretation, every decision and event creates a new, branching universe. This leads to an infinite number of parallel universes where every possible outcome occurs. The daughter universes. Hypotheses suggest that new universes are born from existing ones through quantum processes, creating a family tree of universes with shared ancestry. The ultimate ensemble theory, proposed by physicist Max Tegmark, posits that every conceivable universe exists as part of a grand multiverse, where all possible realities are realized. The anthropic principle multiverse suggests that the conditions of our universe are just one set of many possible conditions. This principle is often used to explain why our universe seems fine-tuned for life. In the quantum foam multiverse, at the smallest scales, space-time is constantly fluctuating, creating temporary, tiny universes that pop in and out of existence. These different types of multiverses represent the diverse and imaginative ways scientists are trying to understand the vast possibilities of existence. Each type offers a unique perspective on how our universe fits into the broader tapestry of reality. The concept of the multiverse, while still speculative, is supported by various lines of theoretical and observational evidence. One primary source of support comes from the theory of cosmic inflation. Inflation predicts the existence of multiple bubble universes, each formed during different stages of inflation. The cosmic microwave background radiation provides indirect evidence for the multiverse. Anomalies in the CMB, such as temperature fluctuations and cold spots, might be explained by interactions with other universes. String theory, a leading candidate for a theory of everything, naturally predicts a multiverse. The vast number of possible vacuum states in string theory suggests a landscape of potential universes, each with different physical laws. Quantum mechanics, particularly the many worlds interpretation, offers theoretical support for the multiverse. This interpretation implies that every quantum event results in the creation of parallel universes, encompassing all possible outcomes. Black holes offer another intriguing possibility. Theoretical work suggests that black holes could serve as gateways to other universes, with each black hole potentially spawning a new, separate universe on the other side of its event horizon. The fine-tuning of physical constants in our universe hints at the multiverse. The anthropic principle suggests that we observe these fine-tuned conditions because only universes with such conditions can support life. In an infinite multiverse, all possible values of these constants would exist somewhere. Mathematical models support the multiverse concept by showing that different mathematical structures can correspond to different physical realities. This theoretical framework suggests that all consistent mathematical structures could represent actual universes. Observations of dark energy and the accelerating expansion of the universe may also provide indirect support for the multiverse. Some models of dark energy involve interactions with other universes, influencing our own universe's expansion rate. Advanced computer simulations based on theoretical physics predict the formation of bubble universes during cosmic inflation. These simulations offer a visual representation of how multiple universes could emerge from a common inflationary origin. Cosmologists study the potential signatures of other universes within our own. These signatures could include gravitational waves, unusual particle interactions, or anomalies in the distribution of galaxies and cosmic structures. The idea of a multiverse is further supported by the concept of extra dimensions in string theory. If these dimensions exist, they could harbor other universes with different physical properties, accessible only through higher dimensional space. Philosophical arguments also bolster the multiverse theory. The principle of plenitude, for example, suggests that all possible realities must exist, supporting the notion of a multiverse filled with every conceivable universe. Theoretical work on quantum gravity and attempts to unify general relativity with quantum mechanics often lead to predictions of a multiverse. These efforts aim to understand the fundamental nature of reality and often imply the existence of multiple interconnected universes. Experimental efforts to detect evidence of the multiverse are ongoing. Scientists are searching for telltale signs in the cosmic microwave background, gravitational waves, and high-energy particle collisions that might indicate the existence of other universes. The multiverse remains a topic of active research and debate. While direct evidence is elusive, the theoretical foundations and indirect observations provide a compelling case for the existence of multiple universes, expanding our understanding of reality and the cosmos. The multiverse theory, while intriguing, faces significant criticism and controversy. Some scientists argue that the theory is untestable and therefore falls outside the realm of empirical science. One major criticism is the lack of direct observational evidence. While theoretical models predict the existence of multiple universes, there is currently no way to observe or interact with these other universes. The concept of the multiverse challenges the principle of falsifiability. Critics argue that if a theory cannot be tested or potentially disproven, it should not be considered a scientific hypothesis. Some physicists worry that the multiverse theory undermines the simplicity and elegance of scientific explanations. They contend that invoking an infinite number of universes to explain our own could be seen as a way to avoid finding more precise explanations for observed phenomena. There is also concern that the multiverse theory relies too heavily on speculative aspects of string theory and quantum mechanics, which themselves are not fully understood or experimentally verified. Philosophically, the multiverse raises questions about the nature of reality and existence. Some argue that the idea of countless unseen universes stretches credulity and complicates our understanding of the cosmos. The anthropic principle, often used to support the multiverse, is controversial. Critics argue that it relies on circular reasoning, using the existence of observers to justify the conditions observed without providing independent evidence. The multiverse theory's reliance on inflationary cosmology is also debated. While inflation is a well-supported theory, its implications for the multiverse are still theoretical and not directly observable. There are concerns that the multiverse theory might lead to a lack of scientific rigor. If all possible outcomes exist in some universe, it becomes difficult to make precise predictions or to test hypotheses about our own universe. Some scientists believe that the focus on the multiverse diverts attention and resources from more promising areas of research that are directly testable and observable. The mathematical complexity of the multiverse theory is another point of contention. Critics argue that the theory requires highly complex and speculative mathematics, which may not correspond to physical reality. There is also debate over whether the multiverse theory offers any practical or predictive power. While it provides a broad framework for understanding different possible realities, it has yet to yield specific, testable predictions about our universe. Despite these criticisms, proponents of the multiverse argue that the theory addresses fundamental questions about the nature of the cosmos and offers a way to reconcile various observations and theoretical challenges. The controversy over the multiverse reflects broader philosophical debates about the nature of scientific inquiry and the limits of human knowledge. It challenges scientists to think deeply about what constitutes a scientific explanation and how we can explore the most profound questions about reality. The debate over the multiverse is likely to continue as our understanding of physics and cosmology evolves. As new theories and technologies emerge, they may provide further insights or challenge the very foundations of the multiverse concept. An infinite universe carries profound implications for our understanding of reality. If the universe is truly infinite, it suggests that space extends endlessly in all directions, with no boundaries or edges. In an infinite universe, every possible event, no matter how unlikely, could occur somewhere. This means that there could be infinite variations of our own world, and even infinite versions of ourselves. The concept of infinity challenges our understanding of the universe's size and scale. It means that no matter how far we travel, there will always be more space beyond what we can see or measure. An infinite universe also has implications for the nature of time. If space is infinite, time might also be infinite, suggesting that the universe has no beginning or end, and that it has always existed and always will. The idea of an infinite universe supports the multiverse theory. If our universe is one of many, and each of these universes is infinite, it expands the scope of what is possible in reality. Infinity affects the laws of physics. In an infinite universe, the constants of nature we observe might be just one set among many, with other regions of space having different physical laws. The concept of infinity intersects with the anthropic principle. It explains why we observe the universe to be fine-tuned for life. In an infinite universe, all possible conditions exist somewhere, and we happen to be in a region where conditions support life. Cosmologically, an infinite universe challenges our understanding of the universe's origin. The Big Bang Theory describes the expansion from a hot, dense state, but in an infinite universe, this event might be just one of many similar events. Infinity impacts our philosophical understanding of existence. It raises questions about the uniqueness of our experiences and the nature of individuality if there are infinite versions of ourselves in different regions of the universe. An infinite universe implies that entropy and the second law of thermodynamics have different implications. In an infinite space, the gradual increase of entropy might lead to a state where new low-entropy regions spontaneously form, suggesting a different kind of cosmic balance. The idea of infinity influences our search for extraterrestrial life. In an infinite universe, the likelihood of life existing elsewhere increases dramatically, making the universe a potentially teeming with life. Infinity also affects our understanding of cosmic structures. In an infinite universe, there could be regions with entirely different structures, from isolated galaxies to vast voids, each varying in complexity and formation. An infinite universe challenges the boundaries of scientific observation. It implies that there are regions of space we will never observe or understand, pushing the limits of what we can know about the cosmos. The concept of infinity forces us to reconsider our place in the universe. It humbles our understanding, showing that what we observe is just a tiny fraction of an unimaginably vast and complex reality. Ultimately, the implications of an infinite universe extend to every aspect of cosmology and philosophy. It expands our perspective, challenges our assumptions, and drives our quest to understand the true nature of the cosmos. Infinity is a concept that describes something without any limit. In mathematics, it represents an unbounded quantity that is larger than any real number. In cosmology, infinity applies to space, time, and the universe's extent. An infinite universe has no edges or boundaries and stretches endlessly in all directions. The idea of infinity also relates to time. If time is infinite, it suggests that the universe has no beginning or end, existing eternally into the past and future. Infinity can be counterintuitive because it goes beyond our everyday experiences. Our minds struggle to grasp something that has no end or limits. In mathematical terms, infinity is used to describe endless sequences or processes. For example, the set of natural numbers is infinite because there is no largest number. Infinity appears in calculus through concepts like limits and infinite series. These mathematical tools help describe phenomena that continue indefinitely or grow without bound. The symbol for infinity, and was introduced by the mathematician John Wallis in the 17th century. It is used in various branches of mathematics to denote unboundedness. In set theory, infinity is explored through different sizes of infinite sets. The concept of cardinality distinguishes between countable infinity, like the set of integers, and uncountable infinity, like the set of real numbers. Infinity also arises in physics. For example, black holes are thought to contain singularities, points where density becomes infinite, and our current laws of physics break down. The concept of infinity in the universe suggests that there could be infinite variations and possibilities. Every conceivable configuration of matter and energy might exist somewhere in the infinite cosmos. Philosophically, infinity challenges our understanding of existence and reality. It raises questions about the nature of the universe and our place within it, suggesting that our observable universe is just a small part of a vast, limitless expanse. Infinity also appears in discussions of the multiverse. If multiple universes exist, and each one is infinite, it expands the scope of what is possible and challenges our notions of uniqueness and identity. The concept of infinity affects our understanding of cosmological events. In an infinite universe, events like the Big Bang could happen repeatedly, creating endless cycles of creation and destruction. Infinity plays a role in the laws of thermodynamics. The idea of an infinite universe challenges the concept of entropy and the eventual heat death of the universe, suggesting that new, low-entropy regions could spontaneously form. Understanding infinity is crucial for exploring the universe's ultimate nature. It pushes the boundaries of science and philosophy, challenging us to think beyond the finite and explore the limitless possibilities of the cosmos. Infinity gives rise to several paradoxes and thought experiments that challenge our understanding of the universe. One famous paradox is Hilbert's Hotel, which illustrates the counterintuitive nature of infinity. Hilbert's Hotel is a hotel with infinitely many rooms, all occupied. Despite being full, it can still accommodate more guests by shifting each current guest to the next room, freeing up the first room. Another paradox is Zeno's paradoxes, which question the nature of motion and divisibility. In one example, Achilles can never overtake a tortoise in a race because he must first reach the point where the tortoise was, which keeps moving forward. The Banach-Tarski paradox in mathematics shows that it is possible to take a solid sphere, divide it into a finite number of pieces, and reassemble those pieces into two identical spheres the same size as the original. The thought experiment of Boltzmann brains suggests that in an infinite universe, self-aware entities could randomly form from fluctuations in a high-entropy state, leading to the question of whether our reality is such a fluctuation. Another thought experiment is the infinite monkey theorem, which states that a monkey randomly hitting keys on a typewriter for an infinite amount of time would eventually type out the complete works of Shakespeare. The grandfather paradox involves time travel. If you travel back in time and kill your grandfather before your parent is born, it creates a logical contradiction, questioning the nature of causality in an infinite timeline. The twin paradox in special relativity explores the effects of time dilation. One twin travels at near light speed and returns younger than the twin who stayed on Earth, highlighting the complexities of time in an infinite universe. The paradox of the infinite universe and the fine-tuning problem asks why our universe has the exact conditions necessary for life. In an infinite multiverse, all possible conditions exist, so our universe's fine-tuning is not unique. The thought experiment known as Schrödinger's cat illustrates the strange nature of quantum mechanics. A cat in a box can be simultaneously alive and dead until observed, raising questions about reality in an infinite set of possibilities. The ship of Theseus explores identity over time. If all parts of a ship are gradually replaced, is it still the same ship? This thought experiment raises questions about continuity and change in an infinite universe. Russell's paradox challenges the foundation of set theory. It considers the set of all sets that do not contain themselves, leading to a contradiction and questioning the nature of infinity in mathematics. The paradox of infinite divisibility asks whether space and time can be divided infinitely. If they can, it raises questions about the fundamental nature of reality and whether there are smallest possible units. The idea of an infinite regress occurs in philosophical arguments. If every event has a cause, and this chain of causes stretches back infinitely, it challenges our understanding of the origin of the universe. The paradox of the omnipotence of God, known as the paradox of the stone, asks whether an omnipotent being can create a stone so heavy that even it cannot lift, questioning the nature of infinity and power. The doomsday argument uses probability to predict the likely number of future human beings. It suggests that given our current position in human history, the total number of humans that will ever exist is not infinite. These paradoxes and thought experiments highlight the complexities and challenges of understanding infinity. They push the boundaries of our knowledge and force us to rethink fundamental concepts in science, mathematics, and philosophy. Philosophical arguments for and against infinity have been debated for centuries, challenging our understanding of the universe and existence. Proponents of infinity argue that it is a necessary concept to explain the boundless nature of reality. One argument for infinity is the principle of plenitude, which suggests that all possible things must exist somewhere. This principle supports the idea of an infinite universe where every conceivable event and entity can occur. Plato's theory of forms also implies a kind of infinity. He proposed that abstract forms or ideas are timeless and unchanging, existing in an infinite realm beyond our physical world. Aristotle, however, had reservations about actual infinity. He distinguished between potential infinity, which is a process that can continue indefinitely, and actual infinity, which he argued does not exist in nature. Immanuel Kant questioned the concept of an infinite universe in his Critique of Pure Reason. He argued that the human mind cannot fully comprehend infinity, as it lies beyond the limits of our experience and understanding. Georg Wilhelm Friedrich Hegel saw infinity as a dynamic process, an unfolding of the absolute. For Hegel, true infinity was not a static concept, but a dialectical movement that encompasses both finite and infinite elements. David Hilbert, a prominent mathematician, argued against the physical reality of infinity with his famous paradoxes. He believed that while infinity is a useful mathematical concept, it cannot exist in the physical world. In contrast, Georg Cantor, the founder of set theory, revolutionized mathematics with his work on different sizes of infinity. He showed that some infinities are larger than others, expanding our understanding of the infinite. The cosmological argument for the existence of God often invokes the concept of infinity. It posits that an infinite regress of causes is impossible, leading to the conclusion that there must be a first cause, which is infinite and uncaused. Conversely, some philosophers argue that infinity leads to paradoxes and contradictions, undermining its validity. They claim that our finite minds and experiences cannot accurately grasp the concept of true infinity. The problem of the infinite past is another philosophical challenge. If the universe has existed for an infinite amount of time, it raises questions about how we ever arrived at the present moment, given an endless sequence of prior events. Infinity also plays a role in discussions of the multiverse. Some argue that an infinite number of universes makes the fine-tuning argument for the existence of God unnecessary, as all possible conditions would exist somewhere. Philosophical skepticism about infinity extends to ethics and decision-making. The concept of infinite consequences challenges our ability to assess the moral weight of our actions, if every choice leads to an endless chain of outcomes. Infinity raises metaphysical questions about the nature of existence. If there are infinite versions of ourselves in different universes, it challenges our sense of identity and uniqueness. Ultimately, philosophical arguments for and against infinity push the boundaries of human thought. They force us to grapple with the limits of our understanding and the profound mysteries of existence, driving ongoing exploration and debate. The concept of an infinite universe profoundly impacts human understanding of our place in the cosmos. It challenges the notion of a finite, comprehensible reality, pushing us to think beyond our immediate experiences. An infinite universe expands our sense of scale. It suggests that the vastness of space and time far exceeds what we can observe or imagine, altering our perception of distance and duration. Infinity also affects our understanding of probability and uniqueness. If every possible event can occur somewhere, it means that our existence and experiences are not unique but part of an infinite set of possibilities. This idea influences philosophical and existential reflections on the nature of life. In an infinite universe, the meaning and significance of individual lives may seem diminished, prompting deeper questions about purpose and identity. The concept of infinity encourages scientific exploration and discovery. Knowing that the universe might be infinite drives the quest to uncover more about its structure, origins, and the laws that govern it. Infinity also impacts theoretical physics. It challenges scientists to develop models and theories that can account for an unbounded cosmos, pushing the limits of our mathematical and conceptual frameworks. In mathematics, the concept of infinity has led to significant advancements. Understanding different types of infinity and their properties has opened new fields of study and deepened our comprehension of mathematical principles. Infinity in the context of the universe raises questions about the nature of reality and existence. It suggests that the observable universe is just a small part of a much larger, possibly infinite structure. The idea of an infinite universe intersects with discussions on the multiverse. If multiple, infinite universes exist, it expands the scope of what is possible and challenges our understanding of reality's fundamental nature. An infinite universe also influences our understanding of time. It raises questions about whether time itself is infinite, and how the concept of eternity fits into our comprehension of the cosmos. The concept of infinity has ethical implications as well. It challenges us to consider the long-term consequences of our actions if time and space are boundless, affecting our approach to sustainability and responsibility. Infinity impacts our cultural and religious perspectives. Many religious and spiritual traditions grapple with the concept of an infinite cosmos, integrating it into their understanding of the divine and the eternal. The idea of infinity inspires awe and wonder. It reminds us of the vastness and mystery of the universe, fostering a sense of humility and curiosity about the unknown. Infinity challenges our cognitive limits. It pushes the boundaries of human thought and imagination, encouraging us to explore new ideas and perspectives. Ultimately, the concept of an infinite universe shapes our understanding of existence, reality, and our place within the cosmos. It drives scientific inquiry, philosophical reflection, and cultural evolution, enriching our quest for knowledge and meaning. Theoretical physics grapples with the concept of infinity in various ways. One of the primary areas where infinity plays a role is in the study of black holes. The singularity at the center of a black hole represents a point of infinite density, where current physical theories break down. In the realm of cosmology, infinity appears in the context of the universe's expansion. The idea of an infinitely expanding universe challenges our understanding of space and time and raises questions about the ultimate fate of the cosmos. Quantum mechanics introduces the concept of infinite possibilities. According to the many worlds interpretation, every quantum event leads to a branching of the universe into an infinite number of parallel realities. String theory, a leading candidate for a theory of everything, relies heavily on the concept of infinity. It posits that the fundamental constituents of the universe are one-dimensional strings that vibrate at different frequencies, existing in an infinite number of possible states. The notion of extra dimensions in string theory further complicates our understanding of infinity. These additional dimensions, beyond the familiar three, suggest that space could be infinite in ways we cannot directly perceive. In the study of the early universe, the concept of cosmic inflation involves rapid exponential expansion, potentially creating an infinite number of bubble universes within a multiverse framework. The infinite nature of space-time itself is a central topic in general relativity. Einstein's equations describe how mass and energy curve space-time, leading to solutions that include infinite curvature, such as those found in black holes. Mathematical infinities are crucial in theoretical physics. Calculations often involve infinite series and integrals, which require sophisticated techniques to handle and make sense of these infinities. The concept of renormalization in quantum field theory deals with infinities that arise in the calculations of particle interactions. Renormalization provides a way to remove these infinities and yield finite, physically meaningful results. Theoretical physicists also explore the idea of infinite energy densities. These arise in scenarios like the Big Bang and black hole singularities, challenging our understanding of the physical laws that govern the universe. The search for a quantum theory of gravity aims to reconcile general relativity with quantum mechanics. This quest involves dealing with infinities that appear when trying to describe gravitational interactions at the smaller scales. Infinity also appears in the context of entropy and the second law of thermodynamics. The idea of infinite entropy raises questions about the ultimate state of the universe and the nature of time itself. Holographic principles suggest that all the information contained within a volume of space can be represented on its boundary, implying a finite representation of potentially infinite information. Theoretical explorations of the multiverse consider the possibility of infinite variations of physical laws and constants. This idea expands the scope of scientific inquiry beyond our observable universe. Ultimately, infinity in theoretical physics challenges our understanding of the universe's fundamental nature. It pushes the boundaries of science, requiring new concepts and mathematical frameworks to describe the infinite complexities of reality. In this video, we've explored the profound question of whether the universe is infinite. We began with a brief overview of the topic, emphasizing its importance in cosmology and philosophy. Understanding the universe's size and shape is crucial for comprehending its origins, structure, and ultimate fate. We delved into the ancient beliefs and myths that have shaped human understanding of the cosmos, followed by the philosophical debates that have persisted through the ages. Early scientific theories laid the groundwork for our current understanding, while religious perspectives have also influenced how we perceive the universe's vastness. Methods of observation, such as telescopes and spectroscopy, have allowed us to gather evidence about the universe's structure and expansion. Despite technological advances, there are still significant limits to what we can observe, leaving many questions unanswered. The distinction between the observable and total universe was another key topic. While we can only see a fraction of the universe, theoretical models suggest it could be far larger, potentially infinite. Key discoveries, like the cosmic microwave background and the expansion of the universe, support this idea. We discussed various theories about the universe's future, including the Big Freeze, Big Rip, and Big Crunch. These scenarios depend on the nature of dark energy and the universe's overall geometry. Each theory has different implications for the concept of infinity. The idea of a multiverse further expands our understanding of infinity. Different types of multiverses, supported by various theories in physics, suggest that our universe might be just one of many, each with its own unique properties and physical laws. Finally, we examined the impact of these concepts on human understanding and theoretical physics. Infinity challenges our perception of reality, pushing the boundaries of science and philosophy. It drives our quest for knowledge and shapes our understanding of the cosmos. If you enjoyed this video, please like and subscribe to our channel for more fascinating explorations of the universe. Don't forget to check out the rest of our videos, where we dive deeper into the mysteries of space, time, and existence. Thank you for watching.